We envisage a scenario where users of anhydrous ammonia can purchase modular microplants online from generic manufacturers. These plants can even be built in a kit configuration, where owners can perform the assembly themselves to reduce cost. The cost of these plants will be under $100,000, and potentially as low as $50,000 per unit. They will be shipped to their location in standard ISO containers, connected to a direct current power source, and run continuously for up to 24 hours per day, to meet all their consumption requirements. These plants will have production capacities of 100 to 300 tons per annum, enough to fertilize 1350 acres. This can be achieved all while producing the compound for less than the present trading price of over $1,000 per ton. If power costs are below 7 cents per kilowatt-hour, a price of ammonia below $600 per ton can be achieved. The hydrogen feedstock can also be sourced from classical sources, such as methane, coal, biomass, and even municipal solid waste. This video provides a descriptive overview of what could be achieved if designers are creative and willing to deviate from convention. It is not prescriptive, but rather it is descriptive, as there can be no strict law on how to design any plant technology. There are many degrees of freedom allotted to the designer, granting him the latitude to make use of a plethora of design options, each tailored to a specific objective, determining where he should channel engineering effort. There are undoubtedly parameters that cannot be exceeded or requirements that cannot be violated or ignored, but there is still immense room to develop technology that can achieve the basic function but that could be arrived at in many different ways. What this video offers is a vision of what can be achieved if a philosophy of design, where creativity and a lack of conservatism is adhered to. Performing an extensive cost, material, and fabrication analysis, and by drawing upon high-volume price estimates from commercial online retailers such as Alibaba.com, high-fidelity cost estimates could be arrived at prevailing market rates. We estimate that small ammonia plants taking advantage of mass-produced largely off-the-shelf components can achieve capital expenditure below $500 per ton of annual ammonia output, surpassing the current benchmark of $1,500 to $2,000. A number of mature technologies from disparate sectors can be merged and concatenated to make this concept viable. A number of challenges arise when downscaling and attempting to integrate with the spasmodic renewable power. Firstly, downscaling imposes a thermal penalty, which will be mentioned in greater detail further along in the video. Secondly, new and improved compressor technologies that can operate at part load will need to be developed. Thirdly, a novel electric heating system will have to be installed in the ammonia catalyst basket to prevent thermal fatigue damage to the catalyst when experiencing sudden temperature fluctuation caused by cycling the plant on and off, according to the demands imposed by the solar or wind facility. This would entail an electric heater of about 150 watts to be integrated inside the main converter, keeping the catalyst basket at a suitable operating temperature. The energy penalty is minimal due to the low thermal conductivity of the insulation. When the electrolyzer is unable to produce enough hydrogen, the reciprocating compressor is simply shut off, along with the flow of hydrogen and nitrogen. The main converter is closed shut, leaving the syngas mixture inside at previous operating pressure. All of the components other than the catalyst would not be sensitive to thermal cycling, as they are merely metallic components that can readily handle sharp thermal gradients. Minimizing this thermal fluctuation would only be needed to prevent negative evolution and modification of the fine crystal structure of the iron oxide catalyst. The proven and mature technologies that form the basis of miniaturized ammonia production are as follows. Number 1, ionic liquid compressors. Number 2, microporous insulation. Number 3, high-activity Wostite catalysts. Number 4, high surface area heat exchangers. Number 5, high-purity part per billion level replaceable gas filtration cartridges. Through the confluence of these 5 technologies, reducing the size of the present-day high-pressure ammonia synthesis process to as little as 100 tons per year is technically viable. This downscaling can be achieved all while maintaining nearly identical efficiency of the large-scale plants, and even reducing its capital expenditure and per-unit output volumetric footprint by significant margins. Introduction. A chemical synthesis system comprises at its heart the active catalytic module, which is usually termed a packed bed reactor, its name redolent of a gravel-like catalyst solidly loaded into a pressure vessel. Solid gravel-like catalysts are most often used as they have high degrees of stability and strength and do not flake or generate powder, which can contaminate reactant products and damage downstream rotary components. The ideal catalyst configuration from a purely catalytic perspective is a fine powder, with a high surface-to-volume ratio, but a fine powder would be extremely cumbersome to contain and prevented from mixing with the reactant products. The major requirements of a chemical reactor are first and foremost the containment of the reactant products, which often being gaseous or liquid and pressurized, must be prevented from leaking or draining from the vessel. The second requirement is to provide adequate thermal management, since most industrial catalytic reactions do not occur at sufficiently high activities at room temperature. An input of heat, often a great deal, is required to sustain the process. This places unique exigencies on the plant designer, as he must find a way to introduce this heat while effectively and efficiently transferring it into the catalyst containment area. In other cases, the molecular combination of the reactant products emits heat, which must be removed continuously from the reactor. This also places design exigencies, such as designing the reactor with sufficient thermal conductivity, or maintaining an adequate surface-to-volume ratio. The third requirement of a chemical reactor is housing and stabilizing the catalyst. A catalyst is potentially fragile and must be prevented from slashing around inside the reactor, incurring damage to its surface morphology through abrasion. A catalyst is subjected to a fluid, a gas, or liquid, which is passing through the catalyst often at high velocity and considerable pressure. If improperly supported, the catalyst will move along with the fluid, requiring the designer to place a solid metal grate to contain it from falling into the open ends of the pressure vessel. In the case of ammonia synthesis, the catalyst is typically configured in a pellet form, with relatively large gravel stone-like catalyst clumps, which are usually formed from crushing the hardened catalyst product after manufacturing. In other catalytic reactions, the catalyst particles are fabricated into a more refined and smooth geometry, such as small cork-shaped pellets, or cylindrical pellets with holes inside to expose additional surface area. Catalyst geometry can be classified into 4 categories: spherical, the pellets are of uniform geometry; cylindrical, with varying length to diameter ratios, or hollow cylindrical; and finally, heterogeneous or crushed gravel-like. The term packed bed reactors typically denotes the same thing as a fixed bed reactor. Most industrial catalytic reactors make use of these packed bed reactor configurations, including those that employ liquid reactant products. Depending on whether the reaction is exothermic or endothermic, in a fixed packed bed reactor, the catalyst will be inserted in a series of tubes fixed inside a larger mother container, which accommodates additional non-catalyst volume, permitting the flow of a coolant. In other cases, where heat is not a concern, the entire container itself may house the catalyst in totality. The former is typically employed in endothermic reactions where heat has to be provided, or highly exothermic reactions, where heat must be purged to prevent runaway temperature. The former case includes steam methane reforming, while the latter includes the World War II-era Fischer-Tropsch process. Ammonia is considered only a mildly exothermic reaction, so heat transfer is not a significant design criterion, allowing modern ammonia plants to be designed with a large catalyst basket that occupies most of the reactor vessel, with heat exchanging occurring between catalyst baskets in a stacked configuration. The overall architecture of ammonia plants has remained unchanged for a century. This is largely attributable to the fact that there is little conceivable reason that anyone could significantly improve upon the process. Most research focus is absorbed by catalyst improvement, which has yielded almost nothing. Little to no research focuses on changing the core reactor technology, as most designers find that there is little presently known to man that could advantage the process. An ammonia plant can be divided into 2 parts: the static portion, consisting of reactors and heat exchangers, and the dynamic portion, consisting of compressors, flow regulators, metering equipment, and sensors. Of the dynamic portion, the compressor is the most elaborate piece of equipment. Present ammonia plants make use of enormous radial compressors using high blade count centrifugal impellers, which typically operate at rotational velocities of below 15,000 rpm. These radial compressors are usually connected directly to steam or gas turbines to avoid the use of reduction gearboxes. In conclusion, there is little hope to perform any changes that are salutary to the technology unless a radically different path is taken. This path, we believe, is modularization, homogenization, and standardization. The prevailing dogma in the chemical production industry, and especially ammonia, is that bigger is usually better. Increasing the size of the plant is commonly understood to bring reductions in cost through economies of scale. Ammonia plants are claimed to enjoy a scaling factor of 0.64 with regards to capex. Those proposing to miniaturize plants are thus flagrantly violating this rule, and are thereby subject to a great deal of scrutiny, and must demonstrate the viability of downscaling by marshalling forward evidence and data in their favor. Larger scale plants mean a bigger upfront purchase, giving more bargaining power to negotiate better deals with suppliers on raw material, labor, and other fixed and soft costs alike. For someone to make a credible argument in favor of miniature production, they not only need to back up their claim that this solution is competitive with existing systems, but also viable from a financial and safety standpoint. Previous efforts at developing miniaturized plants. Despite the fact that the first working ammonia plant was a desktop-size apparatus, miniature plants have been somewhat of a pariah in the industry. In 1909, Fritz Haber and Robert Le Rossignol constructed a miniature desktop-size reactor apparatus, successfully producing 90 grams of ammonia per hour. Contrary to popular belief, miniature ammonia reactors are not a novel technology by any means. Numerous miniature high-pressure reactors have been designed and operated for solar thermochemical energy storage at an experimental and research scale. Most of this research was performed by a team at Australia National University in the 1970s and 80s during the so-called energy crisis. Interest since then has waned. In 1974, P.O. Carden first proposed using ammonia synthesis and decomposition for energy storage. In 1979, Carden published a paper titled, Ammonia Dissociation for Solar Thermochemical Absorbers, in the International Journal of Energy Research. In the paper, he laid out a concept for designing relatively small reformers paired with synthesis reactors to form a reversible thermal storage system. Prior to our efforts, miniature ammonia synthesis was first proposed for a wholly disparate application, namely exploiting the reversible ammonia synthesis and decomposition reaction to store energy for concentrated solar power plants, having little or nothing to do with traditional fertilizer production, which continues to be dominated by legacy producers under a centralized operating model. While there has not been commercial use of Carden's concept, considerable research and modeling has occurred since his paper on the subject, many of them highlighting the design exigencies of downscaling ammonia converters. If one searches Google Scholar using the keywords, solar thermochemical ammonia synthesis, over 16,000 results appear. In a paper entitled, Ammonia Synthesis for Producing Supercritical Steam in the Context of Solar Thermochemical Energy Storage, by Chen et al., they construct a tubular insulated reactor, using an inconel pipe with an inside diameter of 18.88 mm, and an outside diameter of 26.7 mm. The reactor could be operated at a pressure of 30 megapascal and a temperature of 700 degrees Celsius without any embrittlement concerns. The catalyst used was not specified, but judging from the low conversion rate per pass, of 16% at 30 megapascals and 580 degrees Celsius, suggests they used an older generation of magnetite catalyst. The reactor built by Chen et al. Was insulated with 20 centimeters of mineral wool insulation, enough for the reactor to maintain its equilibrium temperature. Aside from the above authors, sundry other papers discuss the use of ammonia synthesis for energy storage, but few details on reactor construction and design are provided. The literature for thermochemical energy storage using ammonia can be drawn upon and serve as a blueprint for prospective designers of small-scale plants for fertilizer production, providing the theoretical foundation for miniature production. The requirements of thermochemical energy storage closely parallel that of small fertilizer plants. Many energy storage applications require very small scales, such as 1 kilowatt or less. Such reactors are subject to the same thermal and compression challenges that reactors for distributed fertilizer production would encounter. As is well known, ammonia reactors are high-pressure devices and thus must be designed to highly stringent design criteria to ensure the safety of operators and personnel surrounding the vicinity of the hazard zone. In spite of this, there is a tendency to overestimate the difficulty and engineering challenges associated with constructing and maintaining these pressure systems. The maximum pressure encountered in an ammonia plant is approximately 30 megapascal, or 4,350 psi. Inconel 625 has a yield strength of 472 megapascals at 500 degrees Celsius, a reactor vessel with an inside diameter of 104 millimeters, and an outside diameter of 134 mm, will experience 171 megapascals of von Mises stress at an operating pressure of 33 megapascals, rendering a safety factor of 2.76. Inconel 625's yield strength only declines 20% from room temperature to 500 degrees Celsius. Pachari Technologies has performed FEA analysis using Altair SimSolid for a 13-liter microammonia converter, enough for many hundreds of tons of ammonia per year. A maximum stress of 80 megapascal is encountered at 200 bar of operating pressure, using Inconel 625. The safety factor based on yield strength is 5 times, based on ultimate tensile strength, the safety factor nearly doubles to 8 times. The approximate yield strength at a 0.2% offset for Inconel 625 is 420 megapascal. The approximate weight of the reactor in question is 250 kilograms. While Inconel 625 is ideal from a strength and reliability perspective, it is not the most desirable option from a manufacturing perspective, due in large part to its high Rockwell hardness, which makes it very difficult to machine. Stainless steel 304 has a sufficiently high yield strength at 450 degrees Celsius to warrant its use. Since stainless steel's manufacturing is much smoother due to its softer nature, a somewhat lower nickel content alloy is often desirable for ease of manufacturing. Since welds weaken the morphology of the part, the ideal manufacturing process is to take a solid round bar, bore the center volume similar to barrel rifling, and use a lathe to remove the inner portion between the two flanges, leaving a solid component free of welds with extremely high strength, resulting in stellar safety performance. The approximate size of a 13-liter reactor vessel is 300 mm wide and 1,400 mm tall. This is for a reactor that is capable of producing 1.26 tons of ammonia per day, at Wustite catalyst activity levels at 200 bar. When the reactor is wrapped in microporous insulation, an additional 10 centimeters of diameter would be added. The cost at volume for the converter should converge to below $5,000 if stainless steel is used, and around $10,000 for Inconel. In the current industry standard, a 600-ton per year plant is considered small. In these conventional plants that have been in use since the 1930s on a commercial scale, the dominant cost contributor is the feed gas compressor, which accounts for over 50% of the capital expenditure of some plants, excluding the natural gas reforming system and air separation plant. Truly small-scale production would entail a plant as small as 100 tons per year, designed to fit inside a 20-foot ISO container which can be placed on a semi-trailer and transported anywhere in the world. The plant would be designed to make use of only commercially available parts and components, minimizing custom fabrication to lower cost. Besides economies of scale providing cost savings, large plants are also touted to be more efficient, but upon further examination, this doesn't necessarily need to be the case, provided design modifications are made to minimize changes in thermal flux encountered when downscaling. Since the development of the modern Haber-Bosch industry, the notion of small plants has been the subject of ridicule in the industry. No serious efforts or successful attempts at designing and manufacturing a small plant have been made to this date. Prior efforts at bypassing classical high-pressure systems such as using electrochemical, plasma, or novel catalysis have usually been met with failure and abandoned. Most of these efforts ended at the research stage and failed to enter commercialization. The only genuine improvement in ammonia synthesis in the past century has been the discovery of Wustite catalysts by Zhejiang University of Technology in the 1980s. Critics of small-scale production usually lay criticism by adducing the reduced efficiency brought about by downscaling. When discussing the energy efficiency of an ammonia plant, there must be a clear understanding of what definition is being used. The actual synthesis gas reaction is an exothermic process, releasing 46 kilojoules per mole, or 0.75 kilowatt-hours of synthesis gas formed. The energy needed to maintain a synthesis gas operating temperature of 450 degrees Celsius, in contrast, is only 0.406 kilowatt-hours per kilogram of synthesis gas. This means an excess heat of 0.304 kilowatt-hours per kilogram is emitted during the formation of 1 kilogram of ammonia. This excess heat in large plants can be recovered with a steam turbine to cover a substantial portion of the compression energy. Theoretically, ammonia is a liquid at 300 bar at below 130 degrees Celsius. This temperature difference of 320 degrees Celsius from the 450 degrees Celsius operating temperature represents 0.30 kilowatt-hours per kilogram of synthesis gas. Unfortunately, despite the thermophysical calculations stating that at 300 bar, ammonia is a liquid at 130 degrees Celsius, in the real world, it has to be cooled down further to around 26 degrees Celsius at an operating pressure of 292 bar. For lower pressure systems, the feed gas must be cooled to below ambient temperature. At an operating temperature of 450 degrees Celsius, this corresponds to an hourly heat rejection requirement of 1.4 kilowatt-hours per kilogram of ammonia. For a 10 kilograms per hour plant, a high-pressure liquid ammonia-cooled heat exchanger, with a high specific surface area, would reject 60 kilowatt-hours using 5 mm diameter non-pressure bearing tubes. The thermal conductivity of hydrogen at 500 degrees Celsius is over 0.3 watts per meter Kelvin. For a heat exchanger tube size of 5 mm, a specific heat flux of 66 kilowatt-hour per square meter is achieved in a convenient heat exchanger configuration. The specific surface area of the heat exchanger is 159 square meters per cubic meter. Since the small-scale plant deviates in many respects from the established design doctrine of mega-scale plants, one distinguishing feature is the heat exchanger and catalyst bed separation. In classic plants, the converter accommodates the heat exchangers as well as the catalyst basket. For a miniature plant, it is more convenient to design the components as separate modules, reducing their size and making their fabrication more convenient. For the ammonia liquefaction heat exchanger, the cooling and heating exchanger can be made in two separate pressure vessels. A single tubular heat exchanger is used to cool the exit stream of ammonia to the condensation temperature. This liquefied ammonia then flows into a small pressure chamber, where the liquid is allowed to drain down into a collector tank. Then the remainder of the unsynthesized reacted product is passed through the temperature-raising heat exchanger using the newly warmed thermal medium. This can include hydrogen gas, gaseous ammonia, helium, or liquids such as glycol if residence time is kept very short. Liquids with boiling temperatures too much below the operating temperature of the main synthesis reactor are unlikely to be suitable, leaving high heat capacity gases as the most realistic option. It should be emphasized that since the objective of miniaturized production is to reduce cost and to accommodate distributed production, in order to adhere to the philosophy of COTS, an abbreviation for commercial off-the-shelf, the designer should try his best to design the plant around the available parts. This entails doing everything possible in keeping the design features in consonance to the components and supplies that are readily procurable without excessive customization. This is in stark contrast to designing it in such an elaborate fashion as to make the plant dictate the type of parts and components required. The preponderance of an ammonia plant's complexity emanates from its auxiliary systems, which consist of the high-pressure compressor, such as a diaphragm type, which features dual use and hence wide commercial availability. This leaves the air separation plant and gas purification, which are also multi-use systems that are mass-produced especially at reduced volumes. For example, small air separation plants are commonly used to produce medical oxygen, but these same plants can be tailored for nitrogen production with the same carbon molecular sieves installed. In reality, an ammonia plant is merely comprised of rudimentary components, namely the pressure vessels, a multitude of threaded fittings forming the plumbing system, and vortex flow meters and automatic valves forming the gas monitoring and regulation system. In light of this, the designer should be willing to sacrifice design freedom to harmonize the plant with the availability of mass-produced components. Thermodynamics and kinetics. Using high-activity Wostite catalysts at a space velocity of 30,000 hours at 30 megapascals, the conversion per pass is as high as 30%, requiring a total of 1 kilowatt per kilogram, to reheat the gas upon cooling and separation, a total of 3.3 times to achieve full conversion. As mentioned before and discussed in further detail in a later part of the video, in the absence of sophisticated insulation technology and its effective integration with the catalyst modules and heat exchanger, small-scale production suffers an energy penalty, due to requiring a substantial portion of the reaction's energy budget to be expended to maintain reactor temperature. This number could amount to nearly 1 to 1.5 kilowatt-hours per kilogram of NH3, a prohibitive figure which has served to strongly dissuade prospective designers and engineers from exploring the option of downscaling ammonia reactors, allowing the industry to continue to dominate with classic production technology. While losses from synthesis gas heating can be considerable for a small uninsulated reactor, the fact remains that the preponderance of the energy consumption of ammonia production is not found in the formation of the product, but rather is dominated by hydrogen production, with synthesis gas compression trailing far behind. Over 90% of the total energy consumed in the process is related to producing hydrogen, which accounts for 75% of the volume of the reactant gas, but only 17.8% of its mass. Since natural gas is the most common hydrogen feedstock, we can estimate the energy intensity of this process. Natural gas reforming is a highly endothermic process, requiring 206 kilojoules per mole of methane. The reaction is as follows: CH4 plus 1H2O equals 1CO plus 3H2. This corresponds to 10.72 kilowatt-hours per kilogram of hydrogen produced, or roughly 32% of the lower heating value of the final hydrogen product. Electrolysis, on the other hand, involves a net energy loss, since water is a highly oxidized molecule. The total energy required for water splitting is lower in the vapor phase. In this phase, the number is 241.8 kilojoules per mole. In the liquid phase it is 285.83 kilojoules per mole. Since commercial electrolyzers almost exclusively split water in the liquid phase, the number of 285.83 kilojoules per mole is used. This translates to 4.4 kilowatt-hours per kilogram of water split. Since H2O is exactly 11.19% by mass hydrogen, the minimum energy consumption to split water is 39.39 kilowatt-hours per kilogram. Since 178 kilograms of hydrogen is required to produce 1 ton of ammonia, assuming no losses to the atmosphere, the minimum energy consumption is around 7,000 kilowatt-hours. Nitrogen must then be compressed from 1 bar to roughly 1 megapascal, to facilitate the pressure swing adsorption process needed to produce the highly pure nitrogen. This is a convenient feature, since the diaphragm compressor for the synthesis compression requires an inlet pressure of at least 1 megapascal to operate effectively. Using the best available data, a multi-stage inter-cooled piston compressor with a mechanical efficiency of 80%, an inter-stage pressure drop of 0.35 bar, and a volumetric flow rate of 1 meter per second, would consume around 450 kilowatts of power. Since nitrogen is 78% of atmospheric air, 3,510 kilograms of nitrogen would be compressed to 1 megapascal using 450 kilowatts in 1 hour, or around 0.128 kilowatt-hours per kilogram N2. For 1 ton of ammonia, 822 kilograms of nitrogen is required, so the PSA system would use 98 kilowatt-hours per ton of NH3. The synthesis gas compression emerges as the second most energy-intensive step in the ammonia synthesis process after hydrogen production. For centrifugal compressors installed on extant large-scale plants, the compressors draw 25,800 kilowatts of power. For a 2,200 metric ton per day plant operating at 200 bar, translating into roughly 0.28 kilowatt-hours per kilogram of synthesis gas. In traditional ammonia plants, the hydrogen exits the steam reformer at up to 5 megapascal, and while the nitrogen produced from cryogenic distillation can in theory be compressed for free, since the liquid gas can be evaporated in a confined chamber, but since most of the volume is occupied by hydrogen, at a 3:1 ratio, this cannot be performed feasibly. For small-scale reciprocating compressors, The efficiency is surprisingly close to the benchmark centrifugal machines, with the best-in-class reciprocating compressors drawing around 0.20 kWh per kilogram of N2. For hydrogen compression, a realistic figure is around 3.5 to 4 kW of power per kilogram of hydrogen at 300 bar, using intercooled reciprocating piston compressors, translating to just under 600 kWh per ton of ammonia. Since the principal bulk of energy consumed in ammonia synthesis pertains to the production of the hydrogen feedstock, scale offers little to no opportunity to reduce energy demand other than easily avoided differences in heat transfer. Therefore, we can conclude that there is no intrinsic feature of mass-scale production that facilitates a marked improvement in process efficiency if heat transfer is held constant. This leaves only extraneous factors at play, largely isolated to the auxiliary systems, as opposed to the core reaction process. In fact, one can argue that since large-scale production exclusively makes use of centrifugal compressors, which have theoretically lower efficiency than an optimized near-isothermal reciprocating compression system, such as novel ionic liquid compressors mentioned later in greater detail, a small-scale plant could in theory achieve best-in-class efficiency numbers, paralleling the industry benchmark multi-thousand-ton-per-day plants. To better elucidate the advantages and disadvantages of small-scale production, we need to thoroughly investigate how scale affects the efficiency of the actual reaction itself. Since ammonia reactors must sustain high temperatures, as we have already mentioned before, a larger reactor will experience a reduced thermal loss to the surrounding environment due to the square-cube law. This obliges the designer of a small-scale plant to employ low thermal conductivity heat-resistant insulation, to counterpoise the additional thermal flux resulting from a higher surface to volume inherent to a small reactor vessel. Other than changes in thermal flux, a small penalty will be encountered due to the phenomenon of roughness-induced turbulent pressure drop. Since a small plant uses hosing or piping that are smaller in diameter, the roughness of these internal passageways will cause a pressure drop across the circuit, and since the ratio of surface to volume is greater, more gas will be exposed to the rough outer surface and will become turbulent, causing its velocity to increase and pressure to decrease. This can be mitigated by using extra smooth internals, or keeping the gas-hourly space velocity at a lower number. The best way to reduce pressure drop is by increasing the internal volume of the flow path by using larger diameter hoses and or keeping the distance between compression and final condensation as short as possible. This can be achieved by intelligent placement of components in the module by using the least circuitous orientation. Thermal management systems. To minimize thermal losses, Pachari Technologies has designed a novel insulation system utilizing microporous insulation that encapsulates the high-temperature ammonia reactor module. The entire converter and exchanger assembly is wrapped with many centimeters of rounded insulation board, and sealed with high-temperature sealant. Microporous insulation is made from silica and aluminum oxide powder or fibers, whose interconnecting pore size is kept below the mean free path size of air molecules. The density of microporous insulation is typically between 280 and 320 kg per cubic meter. The specific heat capacity of the insulation material is around 900 joules per kilogram Celsius. Using microporous insulation, in our case study, produced by Luyang Energy Saving Materials Limited, which retails for $5 to $10 per kilogram, thermal flux can be brought down close to zero depending on the desired thickness. This microporous insulation can maintain a low thermal conductivity of between 0.023 watts per meter Kelvin at a temperature of 300 degrees Celsius, increasing to only 0.03 watts per meter Kelvin at 600 degrees Celsius, 150 degrees hotter than what is encountered in a Haber-Bosch reactor. Unifrax, located in Tonawanda, New York, offers a flexible microporous insulation called Excelfrax 1800 FlexLiner, which can be conveniently wrapped around cylindrical components or hoses, without custom shaping. Using 1 centimeter of insulation wrapped around the vessel, the heat flux for a 10 kg per hour, or 87 ton per year reactor, would only amount to 120 watts, corresponding to 1.7% of the total hourly heat flux. For a 53 kg per hour NH3 reactor, approximately 1,400 mm tall, with a surface area of 1.3 square meters, with 10 centimeters of microporous insulation installed, would shed around 135 watts, or 135 watt-hours, corresponding to a heat loss percentage of 0.0036% of the hourly heat flux. In light of these numbers, the argument that heat losses handicap small-scale reactor development is falsified. With this insulation technology, it's increasingly difficult to argue that downscaling somehow intrinsically involves an energetic penalty. This would only be the case if the designer was sloppy and failed to utilize the necessary design solutions. A large-scale ammonia converter has a diameter of up to 3 meters. This size reactor has a surface-to-volume ratio of roughly 1.72. The miniature reactor has a surface-to-volume ratio of 35, or roughly 20x higher, while the volume of the reactor is 5,500x larger. For the large-scale reactor with 50 cubic meters of catalyst volume, the total thermal budget is 113,000 kilowatt-hours. The heat flux through the reactor wall is 9,800 kilowatt-hours without any insulation. This corresponds to 8% of the hourly heat flux, or 24 times greater than our insulated microreactor. For the small-scale plant's main converter, there are two methods available to the engineer for fabrication. The first option is the rifling or boring method, which involves making use of a monolithic piece. The second, more convenient, but less robust option, is the welding and bolting of flanges. In this manufacturing procedure, the reactor vessel would be constructed out of stock stainless or Inconel seamless pipe. Inconel steel pipe would then be cut to length with plasma cutters or a water-cooled saw blade, and two thick flanges with bolt holes would be welded to each end. Since the engineer would not want to rely on welds to hold the two flanges, which are subject to immense upward pressure, the two flanges would be held together by running threaded rods bolted to the two flanges, transferring the outward flange pressure to static tensile load on the rods. At the end of the flange, a gasket is mounted to ensure a proper seal. The gasket is replaced during catalyst refurbishment or reactor inspection. The diameter and length of the pipe are chosen based on the volumetric capacity of the catalyst that is required to produce the desired amount of ammonia hourly. The seamless pipe option would be considerably cheaper than the lathe and boring process, but it is up to the designer to make use of the most suitable manufacturing process, as long as the end result of a high safety factor is attained. The excessive cost of hydrocarbon-based ammonia. The ammonia industry is subject to technological evolution, like any industry and sector. In this case, the technological evolution at hand is the need to adapt to a new environment where low-cost direct current from photovoltaic and advanced wind turbine technology can be used to feed alkaline electrolyzers, to substitute the depletable methane reserves. In today's ammonia industry, large producers have monopolized the market, and charge far in excess of what natural gases cost as the principal feedstock would predict. For example, in January 2022, the price of anhydrous ammonia was $1,500 per ton, while the price of natural gas was trading for $5 per thousand cubic feet, or roughly 26 cents per kilogram. There is approximately 19 kilograms of natural gas in 1,000 cubic feet or a million BTU. The price of producing hydrogen from natural gas is only $1 to $1.50 per kilogram. Around 3 kilograms of methane is required to produce 1 kilogram of hydrogen using steam methane reforming. Therefore, the price of ammonia should be still below $500 per ton. Up until just a few months ago, natural gas in the US has averaged below $5 per million BTU. Since ammonia is only 17.8% hydrogen by mass, if we divide the price by this fraction, ammonia comes to nearly $9,000 per ton, an insanely high price for mere hydrogen. Since hydrogen is produced from natural gas which up until recently sold for $5 per million BTU, or just under 30 cents per kilogram, this would be a price of $300 per ton. Dividing this by the hydrogen fraction of methane of 22% equates to only $1,360 per ton. In other words, ammonia's hydrogen content is nearly 7 times higher than the value of the hydrogen itself. 82% of ammonia is nitrogen, which is effectively a free commodity. This severe price imbalance is engendered by industry consolidation. A capex for a greenfield Haber-Bosch plant of below $1,500 per ton per year is typical. If amortized to as little as 15 years, this yields a capex component per ton of NH3 of $100. There is very little information available on the internet on the typical lifespan of an ammonia plant, but the available evidence seems to suggest the lifespan of the Haber-Bosch plant is impressive. Phoenix Equipment in New Jersey acts as a broker for chemical plants online. Of the 9 anhydrous ammonia plants currently for sale on their website, the average age of the plants is 43 years old, with many still in operating condition. Ammonia plants feature only one dynamic system, that is a system with moving parts, the synthesis gas compressor. The rest of the plant consists of pressure vessels, pipes, valves, and heat exchangers. These components are not subject to dynamic stresses, but rather a combination of thermal and corrosive stresses. With proper material selection, corrosion and thermal stresses can be mitigated, affording a long-lived plant. While the labor intensity of an anhydrous ammonia plant is substantial, especially for very large plants, the net labor contribution to production cost is insignificant. According to a 2013 thesis, the total labor intensity of anhydrous ammonia plants comes to around 1 man-hour expended per ton. In a developed country, 1 man-hour could be over $30 to $50, adding a trivial cost to production of at least $30 per ton. In countries where wages for plant operators are barely $15 per hour, this number falls below a figure that would warrant serious consideration. Distributed plants, on account of their simplicity and their high automation potential, can reduce labor costs to effectively zero. Hydrogen production costs from methane. Methane contains 22% hydrogen by mass. The raw stoichiometric ratio would predict that 4.54 kilograms of methane are required to produce 1 kilogram of hydrogen. But since the carbon monoxide is converted into additional hydrogen through the water-gas shift reaction, additional free hydrogen is extracted with only water vapor needed as an energy source. For reference, Capsum Industrial Solutions located in Nanjing, built a 600,000 ton per year plant for $650 million. This includes hydrogen gas production and purification, since by definition, an ammonia plant cannot be a standalone unit. The Capsum plant capex is approximately $1,083 per ton per year. If this figure is amortized over 20 years, it would come to only $54 per ton, including 5% annual maintenance, adding another $54 per ton. Since the facility is in Asia, labor costs are expected to be somewhat lower and therefore cannot be used as a reference for domestically built plants, but this is precisely where the equation becomes interesting. Since modularized plants can be transported by road and dropped into place, rather than site-erected, we can take advantage of global marketplaces to offer the most competitively priced plant. Existing ammonia plants often include a steam methane reformer in their construction, and thus a considerable portion of the maintenance cost is related to the steam methane reforming system. In the Pachari containerized plants, since only the alkaline electrolyzer is relied upon for hydrogen generation, which is a low-temperature system with long life, minimal maintenance is needed outside of the 10-year alkaline stack electrode refurbishment. Steam methane reformer capex. Steam methane reformer technology, much like alkaline electrolysis, is dependent to a large extent on the market price of alloys with a high nickel fraction. These include Inconel, Incalloy, Hastelloy, and stainless steel, to name just a few. Steam methane reformers may operate as high as 1000 degrees Celsius, and use nickel-based catalysts usually supported on alumina. HK40, comprised of 22% nickel, is the industry standard alloy for reformer tubes. SMR reformer tubes are typically centrifugally cast, as opposed to forging, due to specific grain structure optimization requirements. From an engineering perspective, our micro-wind or solar-driven plant must not only successfully downscale the existing Haber-Bosch process, but it must also demonstrate a successful alternative to steam methane reforming. Steam methane reforming is one of the most successful and proven high-temperature catalytic plant technologies in the world after Haber-Bosch, with immense production volumes, used not only for ammonia production, but also for petroleum hydrocracking and methanol production. A fair comparison between methane-fueled large-scale Haber-Bosch and downscaled Haber-Bosch using electrolyzers is required. In order to perform this comparison, data on the capex of steam methane reformers is curated from available sources. Chengdu New Energy Technology Co. sells a 50,000 cubic meters per hour steam methane reformer for $50 million. The price per kilogram over a 15-year period would be only $0.093 per kilogram of hydrogen produced. In February 2020, Air Products began construction of a $500 million hydrogen production facility in Saudi Arabia with a production capacity of 413,525 kilograms of hydrogen per day, yielding a per kilogram cost of 22 cents over 15 years. Adding maintenance at 5% of initial capex, an additional 16 cents per kilogram can be added. In 2016, Air Products built a 289,000 kilograms per day plant for $400 million, yielding 25 cents per kilogram over 15 years. With this estimate of benchmark OPEX and CAPEX, with a natural gas price of roughly 30 cents per kilogram, 90 cents per kilogram would be the raw feedstock cost for the reformer, with another 30 cents for CAPEX, and another 16 to 25 cents for OPEX, yielding a hydrogen price of $1.50 to $2 per kilogram, or $267 per ton of ammonia. Are these numbers realistic? In 2019, S&P Global Platts estimated the average bulk resale value of hydrogen was 79 cents per kilogram, based on the price of methane reforming from the Netherlands with a purity of 99.9%. Since we have validated our crude cost estimates based on adducing the price of the raw material, and the maintenance and acquisition cost of the plant, we can be more confident that the numbers used to compare with alkaline solar or wind electrolysis are realistic market prices. To summarize, comparing these natural gas costs, ammonia prices remain excessively high despite relatively low natural gas prices, suggesting a high degree of industry consolidation, which provides a rationalization for developing a distributed production model. If ammonia were merely selling entirely at cost, that is, it wasn't any more expensive than natural gas, there would be little incentive for farmers to produce it themselves and take on the additional hassle of maintaining a plant on their premises. For the fertilizer market, this elevated price is tolerable as the cost contribution of fertilizer to the total cost of producing the major agricultural products, such as soybeans, wheat, and corn, is only roughly 10 to 15%, and this is including potassium and phosphorus fertilizers, not just nitrogen. These numbers are dated from 2019. The number today is expected to be somewhat higher since ammonia was retailing for $450 to $500 per ton in 2019, while today it is 3 times this price. While agriculture currently accounts for the vast majority of ammonia consumption, the future demand for ammonia may increasingly shift to fuel and energy use as the world tries to find substitutes for hydrocarbons. Presently, this seems to be motivated in large part to reduce carbon emissions to mitigate putative global warming. A more rational justification is rather to secure the long-term sustainability of energy-intensive society by generating a hydrocarbon-free dense energy carrier that can be produced indefinitely from water using photovoltaic or wind energy. There has been much speculation in the nascent ammonia energy community that this caustic fertilizer would someday join the club of liquid hydrocarbons and perform the heavy lifting as the fuel of the future to power ships, heavy-duty vehicles, and provide an energy-dense storage medium to transport energy long distances by tanker. This is largely under the presumption that emissions must be reduced for climate concerns, but we are primarily interested in offering farmers and potentially in the future, fuel users, a viable production source, irrespective of government policy or carbon dioxide concerns, which are likely to be unfounded. The fact is that today, there is no application for ammonia as a fuel outside of highly niche applications. One of the only known applications of ammonia as a commercial fuel is to power alkaline fuel cells to generate electricity for rural cell towers in South Africa. In these specialized settings, ammonia is chosen not based on intrinsic energetic, emission, and/or overall performance characteristics of the molecule as a fuel source, but for extraneous reasons, exclusively to prevent thieves from stealing the fuel. The theft of rural cell tower fuel is an endemic issue in South Africa. Engineers have been forced to employ unconventional tactics to combat it, One of them is by using a foul fuel that few people dare approach and or have little use for, since ammonia cannot readily be sold or reused like diesel fuel. In the cell tower market, companies like Gencell in Israel market a nickel-based reformer and alkaline fuel cell package. For ammonia to become competitive with liquid hydrocarbons, it must first reach price parity with existing fuels. This may seem strange considering current ammonia is produced from these very same hydrocarbons, but once again, this paradox illustrates the unique market conditions in the ammonia industry which contributes to the commodity's price premium over its feedstock. The Herfindahl-Hushman index is commonly used to evaluate the degree of industrial concentration of a given sector. Ammonia ranks at 2378, considered very high, with three producers, Coke, Ura, and CF Industries claiming 75% of the entire market, leaving little room for new entrants. The prospects of ammonia falling in price back to pre-COVID levels is uncertain and may only occur with a significant competitive stimulant. None such appears on the horizon, leaving distributed production as the only contender. In a paper titled, Market Concentration and Pricing Behavior in the Fertilizer Industry, A Global Approach, by Manuel A. Hernandez, the ammonia industry's level of industrial concentration is analyzed and the conclusion is drawn that the industry is far from a perfect equilibrium competition, where products sell at production cost plus a small margin. Since ammonia is an energy-dense fuel, its use will be more attractive for heavy-duty vehicle applications. At the present time, the price of over $1,500 per ton is far too prohibitive for energy storage or transportation. While ammonia sells for $1,500 per ton, oil and natural gas sell for only $730 and $420 respectively, and this isn't even adjusting for ammonia's mass ratio, as we mentioned previously, considering ammonia is only 18% hydrogen with the remainder being comprised of free air. It is quite remarkable this outrageous condition is tolerated. For electrolysis-based ammonia, the present costs would be much higher than steam reforming of natural gas, since in most parts of the world, commercial electricity is generated for at least 10 cents per kilowatt-hour. Moreover, the capex of present-day alkaline electrolysis units is in excess of $1,000 per kilowatt, prohibitively high, effectively forbidding its use outside of niche sectors where high-purity hydrogen is required on site. In order for ammonia to compete with hydrocarbon fuels, the hydrogen produced from the electrolyzer should ideally be under $2 per kilogram, or around $350 to $400 per ton, roughly at the price of natural gas, which is a comparable gaseous fuel. Thankfully, this number is readily achievable as long as electrolyzer plants can be produced closer to material costs. For the wind or solar-driven plant, the capex of the electrolyzer stack and its ancillary components has to be included in the total capex of the ammonia plant. Now let us turn to discussing the price of the major constituent auxiliary systems of the NH3 plant. The cost of pressure swing absorption nitrogen production also has to be included. While the initial capex of a PSA system can be substantial, the levelized production cost per kilogram of nitrogen is negligible. If synthesis gas production system cost is excluded, the single biggest contributor is the compression system, both in terms of operation costs, energy consumption, and the initial capex of the compressor set. After compression systems, the biggest contributor is the air separation plant. The current market price of pressure swing absorption nitrogen generators translates to around $43 per ton per year NH3. For a 100 cubic meters per hour unit, the selling price is $57,900 for a new Chinese-made unit as of 2021. Prices for Western units were not sourced. The price was ascertained from the RFQ function available on Alibaba.com from Suzhou Hyundai Purification Equipment Co. Limited. For a smaller scale nitrogen generator, Yukingtech offers a 3 cubic meters per hour 99.99% purity food grade nitrogen generator for $2,600. This would translate into roughly $66 per ton for the first year of production. Note that a PSA nitrogen generator is simply a container consisting of the carbon molecular sieve, with an air compressor to pump air in and out of the tank. A series of valves are then used to modulate the flow of air into the two sieve containers. Kaiju Shunli Molecular Sieve Co. Limited produces the SLU-HP 100 molecular sieve with a purity of 99.9995% at a price of $9.50 per kilogram. The productivity of this particular sieve is 95 cubic meters of nitrogen per ton of sieve per hour. For a 100 ton per year plant, around 0.37 cubic meter of sieve is needed, with a density of 650 to 690 kilograms per cubic meter. Around 250 kilograms of sieve would be required at a cost of only $2,400, which is quite insignificant. Compressor capex was inferred by sampling the selling price of diaphragm compressors, and used to roughly approximate the future cost of mass-produced ionic liquid compressors. Since ionic liquid compressors are not currently manufactured by more than one company, one cannot ascertain a realistic capex figure. Extrapolation from existing compressor architecture can provide a more realistic and conservative estimation without overestimating the price. Since ionic liquid compressors are only manufactured by Linde Cryotechnic AG, for hydrogen fueling stations, no cost estimate could be ascertained. Ionic liquid compression, as of present day, remains a highly niche technology and thus likely enormously expensive, leaving much opportunity for new companies to offer the technology to the market. The major challenge for synthesis gas compression is preventing lube oil contamination, which can cause downstream catalyst failure. Under ideal circumstances, cheap, mass-produced oil lubricated compressors could be used, and the oil missed in the synthesis gas simply filtered out using absorbents. Such an option is unlikely to prove satisfactory, judging from the fact that the specialized gas compression industry almost exclusively relies on oil-free diaphragm compressors for purity-sensitive applications such as helium or medical oxygen, making little use of post-compression oil scrubbing options. Non-diaphragm compressors, that is reciprocating oil lubricated compressors, are generally very low-cost and rudimentary devices, widely manufactured. For example, Shanghai Guoxia Compressor Co. Limited manufactures a 150 bar 15.9 cubic meters per hour compressor for 18,000 yuan, or $2,780 per unit. The price per cubic meter per hour is $168, while for diaphragm units it is $533, or roughly 3 times higher. This compressor is the GSW265B model. It's a 3-piston compressor, with a flow rate of 265 liters per minute and uses a 380-volt 50 Hz 5.5 kilowatt electric drive motor. The compressor emits 73 decibels during normal operation and weighs only 160 kilograms. Its approximate size is 94 by 70 centimeters by 54 centimeters. The RPM is 1500. At its rated power consumption, compressing the hydrogen from the electrolyzer at 15 bar to 200 bar, would consume only 0.3 kilowatts per kilogram, while it would use as much as 4.23 kilowatts per kilogram starting from atmospheric pressure, highlighting the considerable energy savings if hydrogen can be pre-compressed using the electrolyzer. The flow rate of this $2,800 compressor would permit a production rate of 168 tons per year, costing only $4.80 per ton per year. Unfortunately, until highly effective oil mist absorbents can be used confidently, such ubiquitous and reliable compressor options are not yet suitable for NH3 synthesis. Pachari Technologies is presently scouring the material literature for compounds that could be suitable for a post-compression oil mist absorbent. When such a material is possibly discovered, a major reduction in ammonia plant capex could be realized. For non-oil lubricated reciprocating compressors that make use of molybdenum disulfide filled, PTFE seals, or piston rings, the lifespan is usually 4,000 to 6,000 hours. For diaphragm technology, costs per flow rate are expected to be higher, but since the synthesis gas density is already considerable after exiting the electrolyzer and PSA module, the net cost per unit flow rate is actually very low. The diaphragm compressor has a much smaller working volume, since the maximum volume is limited by the movement of the flexible metal diaphragm membrane, as opposed to the entire cylinder in a standard compressor. This means for equivalent compressor weight, the diaphragm system has a much lower volumetric flow capacity. Despite this, at larger scales, diaphragm compressors still account for negligible capex contribution. The source for the diaphragm compressor price was chosen based on a quote provided by Sichuan Nuqian Yuan Technologies Co. Limited, a prominent manufacturer of diaphragm gas compressors in China. One of their medium flow models is the GL2-7510-350. The intake pressure is 10 bar, the discharge outlet pressure is 350 bar, and the flow rate is 75 cubic meters per hour. The compressor is equipped with an explosion-proof electric motor rated for 30 kilowatts. This compressor also features water cooling with water consumption in a closed-loop circulation system, circulating 2.5 tons of liquid per hour to maintain adequate temperature management. The estimated outer dimensions of the unit is 1950 by 1400 by 1350 mm. The estimated curb weight of the unit is 1,500 kilograms. The unit price is $39,600 per unit. The price was established through communication with the manufacturer directly in 2021. Accurate price quotes are rarely available online for diaphragm compressors due to their specialized nature, especially from Western manufacturers. The flow rate at 1 megapascal inlet pressure with an average density of 4.2 kilograms per cubic meter corresponds to a capex of only $1.40 per ton NH3 annually. The capex is highly sensitive to the inlet pressure. For example, if the inlet pressure was atmospheric, the compressor is able to compress much less gas by mass, as the flow capacity of the compressor is by volume. Since NH3 synthesis gas is 3 moles of hydrogen at 0.082 kilograms per cubic meter, and 1 mole of nitrogen at 1.25 kilograms per cubic meter, the average density is 0.037 kilograms per cubic meter. The pressure of the PSA unit is around 1 megapascal, and since the electrolyzer can operate as high as 30 bar, the plant designer can leverage the elevated inlet pressure to maximize the productivity of the more expensive diaphragm compressor. Diaphragm compressors can be categorized into two sections, the life-limited diaphragm, and the long-lasting hydraulic piston section, which can operate for tens of thousands of hours with only oil changes required. The hydraulic section consists of a cylinder and piston assembly, which pressurizes hydraulic fluid to drive the metal diaphragm, which compresses the gas on the other end. The standard lifespan for diaphragm compressor diaphragms in MTBO, mean time before overhaul, is limited to around 5,000 hours for standard metal diaphragms, which are usually constructed out of multiple layers of stainless steel sheet for maximum suppleness. The diaphragm sheets are subject to intense fatigue stresses, due to the cumulative stress of the sheet bending on the perimeter of its mounting flange, hundreds of cycles per minute. The diaphragm sheets eventually fail right on the outskirts of the flange clamping location of the diaphragm head. Failure usually begins with microcracks, which gradually grow to major fissures, necessitating the replacement of the unit. If left unchecked, a rupture can cause oil and gas to mix and subsequent downstream contamination if warning sensors are not installed or fail to alert the user. A diaphragm compressor is the worst possible design from a longevity and maintenance standpoint, other than the fact that it is presently the only oil-free and high-purity compression architecture available, until ionic liquid supersedes it. PDC Machines, a high-end American manufacturer, claims a life of 6,000 to up to 8,000 hours for continuous use for their metal diaphragm sheets. The main determining factor in the life of the diaphragm is the pressure differential between the gas and the hydraulic fluid. If the differential is small or non-existent, diaphragm life can be extended significantly. Since the diaphragm itself only contributes a small portion of the overhaul cost, most of the life-limited components would be expected to have a similar longevity profile as an oil-lubricated compressor. Considering that the piston and cylinder are submerged in hydraulic fluid at all times, one could argue they would experience considerably reduced friction compared to conventional compressors, whose piston is operating in an oil-poor environment and exposed to pressurized and often corrosive gases. For this analysis, for the sake of simplicity, we assign a MTBO of 4,000 hours for a conservative estimate. We also assume the overhaul consists of a piston ring replacement, check valve, and connecting rod bushing replacement at 10,000 hours. We also assume the overhaul is equal to 50% of the new manufacturing cost, which is a highly conservative estimate and in reality likely much lower than this figure. This adds 75 cents per ton per year NH3. A personal conversation with David Young from Sichuan Nuqianyuan Technologies indicated a MTBO of 5 to 8 years, depending on the working environment, as humidity and salt air can reduce this number dramatically. Beijing Zhongding Hengsheng Gas Equipment Co. Limited advertises their diaphragms to last 5,000 hours, and the main air valve, which are made by Western firms listed as Mario Kazani SIL or Hoabija, are rated for 8,000 hours before replacement or overhaul is due. Now that we have gone over a brief overview of compressor systems and their attendant techno-economic characteristics, we can move on to the electrolyzer. Electrolyzer costs. Even though current electrolyzer stacks from European companies such as Proton, Nel, Hydrogenics, ITM Power, Provide BV, etc., usually feature stack prices in excess of $500 per kilowatt, if one were to employ an advanced COTS manufacturing strategy, they could easily bring this down to close to the raw material minimum. An electrolyzer price of $100 per kilowatt is chosen for this analysis. In 2006, General Electric estimated at high production volumes, an alkaline electrolyzer could be built for at or below $100 per kilowatt, very close to the cost of manufacturing lithium-ion batteries, which use far more expensive raw materials per kilowatt of capacity. The current situation in Ukraine has only moved nickel prices up $13,000 per ton, which has relatively negligible influence on electrode costs. This price increase has not been driven by economic fundamentals on the demand side, but rather by a sudden supply shock, which is expected to slowly ameliorate, placing downward pressure on the industrial metal. Current electrolyzer costs in China are already below $200 per kilowatt, but can be brought down further with more creative manufacturing options discussed in a separate video. At $100 per kilowatt with a lower heating value efficiency of 91%, available at current densities below 200 mA per square centimeter, this translates to $4,400 per kilogram of H2 hourly. Thus, the capex is $90 per ton of annual NH3. Using the current electrolyzer prices in China of $200 per kilowatt, this increases to $180, far outstripping the negligible compressor and PSA costs. As far as the ammonia synthesis catalyst is concerned, it can be purchased online, including from a large catalyst manufacturer called Liaoning Haitai SCI Tech Development Co. Limited. This company offers a traditional lower-yield magnetite-based product, not wustite, for around $20 per kilogram for bulk orders, such as for a plant catalyst replacement, and for small orders, they are willing to sell as little as 1 kilogram for $200. The seller offered to sell 2 kilograms for $200. Assuming the most conservative estimate, for a 50 kilograms per hour reactor, the catalyst cost would be only $3,000, or $7 per ton per year. Solar farm capex. Before we dive into further detail on the rest of the ammonia plant design, we must discuss the importance of a viable, long-term, and competitive power generation technology. Distributed production would make little sense if we simply went right back to drawing from natural gas wells and expensive steam methane reformers. A new paradigm is called for, and this new paradigm is using direct current electricity from photovoltaic. The economic competitiveness of photovoltaic and wind-sourced ammonia will become increasingly evident as hydrocarbon prices rise. With production from inexhaustible water and air, distributed production becomes feasible, overturning the current business model away from centralized production and improving resilience against volatile hydrocarbon energy markets. Distributed solar ammonia can be thought of as a hedge against the uncertain future of conventional energy sources. The beauty of this technology is instead of being dependent on an inherently volatile commodity, natural gas, which for the most part, is an exhaustible resource, one can pivot towards reliance on an inexhaustible resource, polysilicon. Hydrocarbons are a type of resource that conform to a Hubbert's peak model, that is, they are expected to gradually increase in extraction difficulty over time, forcing producers to invest more capital into their production, hence their prices rise with time. In contrast, distributed production is only reliant on polysilicon as a commodity, which will continue to go down in price with increased production since silica is effectively inexhaustible, comprising around 46% of the Earth's crust. Of course, we must not forget that polysilicon requires energy to produce, of which most presently derives from hydrocarbons, and more importantly, silicon must be reduced with carbon to generate pure silicon metal. Ultimately, silica will have to be produced from carbon that is generated in a closed-loop cycle, through plasma decomposition of methane yielding carbon black, and where this decomposed methane is then produced from carbon dioxide and hydrogen. At the present moment, such a closed carbon cycle remains impractical as coal remains abundant. To produce silicon metal from silica sand, around 1 ton of carbon is required per ton of silicon. The carbothermal reduction of silica uses a heavy carbon electrode to heat the silica and carbon mixture from 1500 degrees C to 1700 degrees Celsius. The specific energy inputs for the process are in the order of 12 to 20 kilowatt-hours per ton of metallic silicon, amounting to $900 per ton, at a power cost of 6 cents per kilowatt-hour. Once the low-purity metallic silicon is produced, it has to be further purified using the Siemens process, where it is converted to silane and subsequently decomposed, consuming an additional 100 kilowatt-hours per kilogram. In 2009, the Siemens process reactors consumed 200 kilowatt-hours per kilogram. This number has dropped to about 80 and is expected to fall below 70. With optimized heat recovery, this number could be reduced to 43 kilowatt-hours per kilogram. With this data, we can roughly calculate the EROI, energy return on energy invested, of a photovoltaic plant. Electricity consumption in cutting and placing the solar cells on the backboard are minimal. The bulk of energy consumption is found in the trichlorosilane cycle. Once metallic silicon of high purity is produced from decomposed silane, it is melted down in an induction furnace crystal grower, where the Czochralski method is used to slowly grow a single crystal ingot. This is done by slowly twisting the ingot suspending in the molten silicon. Considerable energy is needed to keep the silicon at its molten temperature, approximately 300 kilowatt-hours per ton to reach its molten temperature of 1420 degrees Celsius. A typical monocrystalline silicon wafer used in a photovoltaic panel is 180 microns thick, and 156 by 156 millimeters. The power density of a monocrystalline panel is roughly 200 watts per square meter, so 5 square meters are required for a kilowatt. The total amount of polysilicon for a 1 kilowatt panel is thus 2 kilograms, requiring 2 kilograms of coal for reduction. From silica to polysilicon, the entire process consumed 120 kilowatt-hours for every kilogram produced. To be conservative, an additional 100 kilowatts is assumed to be required for the fabrication of the panels and their subcomponents. This includes producing the glass for the cover and the aluminum frame. The EROI can be simply calculated by dividing the panel's yearly power output by the per kilowatt embedded energy. Existing industry data seem to indicate the energy required to produce solar panels is considerably greater than the mere silica reduction and Siemens reactor process alone would indicate. This is due to a number of post-production processes that tally up to a significant number above these core processes. A few estimates place the number as high as 10,000 kilowatt-hours per kWp for monocrystalline panels dated back to 2009. This would mean the panel would have to produce power for over 7 years in a high insolation geography just to pay off the initial energy investment. But since this estimate is old and the photovoltaic industry has made great strides, a lower number is likely today. But despite this mediocre EROI, the cost per kilowatt-hour of monocrystalline or polycrystalline photovoltaic is considerably lower than natural gas, which obviously has immensely higher EROI. In 2008, polysilicon sold for $400 per kilogram, while in 2020, it was less than $20 per kilogram, a factor of 20x difference without any underlying change in the technological or material basis of the process. Distributed production using solar and wind, if properly designed, can offer a more competitive production system. With the availability of low-cost photovoltaic energy without the need for balancing grid demand fluctuation, the requirement for storage is eliminated. This opens up the possibility of producing ultra-low-cost hydrogen even below the price of methane reforming. Photovoltaic technology is chosen not for its greenness, or lack of carbon dioxide emissions per se. Rather, it is chosen because photovoltaic technology, in a purely economic denomination, is an inherently superior form of power generation technology, even compared to ultra-high energy-dense sources such as nuclear fission, who must pay a cost for this impressive energy density. Despite uranium fission being 2,000 times more energy-dense than solar, the price of pressurized water reactors in the United States is nearly $7,000 per kilowatt, and about $3,000 per kilowatt in China. Amortized over 40 years, the LCOE is 2 cents per kilowatt-hour, excluding maintenance and fueling, which adds another cent or so. For a photovoltaic array in a high radiance geography at the current capex of $300 per kilowatt for Chinese-made modules, excluding installation, which raises this number to around $400 to $500, the LCOE over a 20-year life is barely over 1 cent per kilowatt-hour, not including maintenance or degradation. The actual lifespan of a solar installation in a benign environment free of hurricanes, hail, and severe winds is likely in excess of 25 years. This number is quite astounding. The fact that harmless, easy to install and manufacture solar energy is equal if not cheaper than the most technologically advanced and energy-dense form of energy available on Earth, that is nuclear fission with moderated light water reactor architecture, is incredibly promising. Anticipated usage profile of distributed ammonia production. Until ammonia begins its use as a low-emission fuel in the near future, the fertilizer market is presently the biggest opportunity. The size of the ammonia industry is nearly $100 billion annually, with production volumes as high as 200 million tons, nearly 20% of the total production of crude oil. In comparison, this sector is of an immense size with unlimited market potential. Before we go into further ammonia plant design details, we will briefly discuss wind power for distributed ammonia. Pachari Technologies has invented a radically new form of wind turbine support structure that promises to halve the present cost of wind energy, but until then, we will draw from the classic but soon-to-be obsolete wind turbine market. We have discussed this revolutionary technology in a separate video. Since no terrestrial energy harvesting technology is a panacea, in geographies limited by poor irradiance, a greater reliance on wind will be required. In those geographies that have both poor wind and insolation, distributed ammonia can either be foregoed, or transportation from more propitious geographies would still, unfortunately, be required unless higher production costs can be tolerated. A large pipeline infrastructure already exists. Transporting ammonia by pipeline is virtually free. Where pipelines are not accessible, short-distance trucking can be acceptable. It should be emphasized that the point of distributed production is not necessarily just to minimize transport. The point of distributed production is to design ammonia plants that can be more easily installed and integrated in any geography that is rich in wind and solar resources, as well as to capitalize on the mass production potential inherent to the modularized plant. Distributed production is designed as a convenient, modular, transportable package that can be connected directly to wind and solar farms. Transportation from these sites to the final end-use destination still has to be performed in some cases. For example, imagine a single 120 kilowatts turbine is located atop a hill where the wind velocity is the highest. The 20-foot ammonia plant container is then located beneath it to yield 60 tons a year, enough to cover 550 acres at 200 pounds of nitrogen per acre. Existing ammonia technology requires a massive wind or solar farm to be built to provide the gargantuan energy needed to fuel a 1,000-ton per day plant, for example, making the economic case for such a large plant and its attendant prime mover very difficult. Hydrocarbon-based modern ammonia plants are getting larger and larger, with some pushing as high as 3,300 tons per day. This type of plant is far too large to be used even by the biggest farmers and is not practical to construct in very rural geographies where many wind or solar farms may be located. Medium-sized wind turbines can offer a competitive solution for regions with wind speeds greater than 6 meters per second. With Pachari pneumatic self-tension tower technology, discussed in a separate video, wind turbines reaching altitudes as high as 300 meters can be constructed with lightweight composite guide towers, allowing it to tap into 10+ meter per second wind speeds. Pachari pneumatic tower technology can generate DC power with commuted generators for less than half a cent per kilowatt, enabling ammonia to be generated for less than the price of consumer water. Until then, we can examine some existing lower altitude wind turbine models and compare their LCOE to photovoltaic. The Habeho Pevwin New Energy Technology Co. Limited turbine model FD42-400, rated for 400 kilowatts, produces 1,450,000 kilowatt-hours per year at a wind speed of 8 meters per second, and 1,069,000 at 6.5 meters per second. This turbine weighs 25,000 kilograms, has a tower height of 50 meters, and is built to the IEC IIIA design class. The cost is approximately $495,000 per piece. The advertised life of the turbine is 20 years and its extreme wind rating is 52 meters per second. In high wind geographies, for example, Cherry and Grant County, Nebraska, the 50th percentile wind velocity at 50 meters of altitude is 8.2 meters per second. A smaller version by the same manufacturer, the FD25-120, a 120 kilowatts turbine, sells for $180,000 and produces 492,000 kilowatt-hours annually at 8 meters per second and 374,000 kilowatt-hours at 6.5 meters per second. Amortized over 15 years with an average wind speed in these counties of Nebraska, where large quantities of ammonia are presently consumed for corn, the turbine would produce a levelized cost of electricity of $0.024 per kilowatt-hour, yielding an ammonia price of only $192 per ton. In a less windy region where speeds are in the order of 6 to 6.5 meters per second, for example, in Iroquois County, Illinois, with a mean of 6.4 meters per second, the levelized cost of power would be 3.2 cents per kilowatt-hour. The cost per ton of ammonia would thus be $257. If the wind speed is to 4 to 5 meters per second, the LCOE would reach 5.5 cents per kilowatt-hour, or $500 per ton of ammonia. Wind speeds of 5 meters per second at 50 meters of height are available throughout most of the U.S. Midwest. Previous efforts to develop distributed ammonia production technology. Aside from Pachari Technologies, few other experts have realized the potential of small-scale ammonia production using advanced technology except for one person. Richard Straight of Rice University has given a talk on his concept for the miniaturization of ammonia production. He goes on to say, quote, "The small self-contained ammonia manufacturing box, abbreviated AMB, came out of the need for farmers in remote locations containing modest amounts of natural gas and water to produce enough fertilizer for their local needs. Presently, ammonia plants are getting larger and larger. The future, however, is to make small, highly automated plants that are portable, use readily available inputs and produce the products where they are needed. To this end, the new small-scale plant will include all the latest leading-edge technologies that apply, such as microprocessing technology, MPT, process intensification, PI, and automated safety systems. The ammonia plant of the future is contained on one rail car, shop fabricated and contains all the latest technology. To date, the economy of scale has been the way to reduce the cost of an ammonia or methanol plant, but we are at or near the limit of what is possible. Moreover, very few companies need such large plants with their large price tags." Close quote. From a conference paper titled, Ammonia Manufacturing Box, Small Ammonia Plant Design Using Microprocessing Technology and Process Intensification Technology, by Richard Straight. Pachari Technologies views the present situation in a similar manner. But we differ in that we are confident that rather than methane reforming, photovoltaic-based hydrogen production, and eventually, using pneumatic tower high-altitude wind turbines, will actually surpass methane in cost competitiveness, but this has yet to be the case since affordable electrolyzers have yet to be produced due to a small market demand. Additionally, wholesale photovoltaic prices are rarely available to small users who only need a few 100,000 kilowatt-hour annually. In the case of wind, prior to Pachari Technologies' pneumatic tower, conventional steel column-supported wind turbines are too expensive due to heavy material usage and the lack of high-speed wind and poor capacity factors at these lower altitudes. Now that we have briefly covered the energy landscape, critical for producing cheap hydrogen for our plant, we can turn to the fascinating technical details of downscaling. The important question is why downscale? When one begins inquiring into the possibility of downscaling, a surprising number of benefits appear, often seemingly contradictory to established industry dogma. Number 1, ability to integrate with intermittent renewables that are often sparsely scattered across diverse and rural geographies. Additionally, if containerized ammonia plants are built directly at wind or solar farms, significant cost savings can be realized by dispensing with grid connections and long-distance power lines. Number 2, potential to reduce capex with the use of ubiquitous off-the-shelf components. Large is not always better. Scaling presents unique manufacturing and installation exigencies. Components become more difficult and technically demanding to fabricate, raising costs and leaving a smaller pool of suppliers to choose from. This leaves developers beholden to a select number of massive corporations, mainly ThyssenKrupp, Casole, or Haldor Topsoe. A small-scale ammonia plant can be easily assembled using parts, reactor tubes, fittings, valves etc., purchased online from Alibaba.com for wholesale prices. Number 3, breaking the monopoly of centralized legacy producers, Yara, Koch, CF Industries, etc. This enables farmers to produce ammonia for less than the price of current commercially acquired anhydrous from large suppliers. It also provides the agriculture industry with the ability to hedge against future price uncertainty, as well as provide the future option to reduce emissions if necessary. Number 4, portability. Small-scale containerized plants can be moved easily by truck, increasing their long-term value, versatility, and asset recoverability. The plant can be sold quickly since geography is no longer a constraint. For example, if economic conditions change for the worse in a local region, the plant can be moved where conditions are more propitious, or it can even be exported overseas into new and growing markets. The plant could also be installed nearby hydropower facilities to exploit the ultra-cheap electricity available at such installations. Often, small hydropower facilities do not have the room or sufficient power generating capacity to install current large-scale plants, forcing owners to sell their power to the local grid at rock-bottom wholesale prices. The plant could also be used in offshore wind facilities since the critical components are sealed from the elements inside the ISO container. This alone highlights the unassailable superiority of Pachari's miniature plant technology, since it would be virtually impossible to hermetically seal a present-day 1,000-ton scale plant. To suggest such would be an absurdity. The limits of scaling. A critical examination of the frequent claims of scaling-induced cost reduction. Sometimes bigger individual components actually make them more expensive per unit of output. Example, a fixed-tube reactor. When the shell diameter is under 12 feet, it can be built in numerous shell and tube heat exchanger shops around the world. We have identified almost 100 shops in North America alone that are capable of building up to 12-foot diameter reactors. When the diameter gets bigger than 18 feet, as is the case with Shell's reactor, the number of shops that can handle the fabrication, and the weight, drops to a handful, and the cost per tube, a measure of unit productivity, goes up, not down. We have received quotes for reactors under 12 feet in diameter and compared them to quotes for reactors in the 18+ feet range. The cost per unit of reactor volume actually increased with the larger reactor, 18 feet plus diameter. Additional shipping costs and erection costs also follow extremely large and heavy components. The above commentary is from a small company that manufactures Fischer-Tropsch synthetic fuel reactors. Interestingly, they came to the exact same conclusion we did. It should be obvious to anyone who has any understanding of manufacturing that an ammonia converter that is 3 meters in diameter is inordinately more difficult to manufacture than one that is only 100 millimeters in diameter. In fact, a 100 millimeter reactor can be fabricated by any facility that has access to either welded tube, or ideally, seamless pipe produced through the mature Mannesmann rotary piercing process, or better yet, as mentioned earlier, using rifling to bore solid cylindrical bars of raw stock material. One important fact to highlight is a modular plant based on small-scale ubiquitous commercial off-the-shelf components can be built in a factory, taking advantage of the lower prevailing wage rate for factory labor, as well as the markedly improved productivity that accompanies the predictable factory setting. Since large ammonia plants have to be erected on site, labor costs will be considerably higher, due to the higher skill levels, insurance costs, and worker transportation and accommodation requirements, yielding a much more cumbersome, delay-prone, and expensive job site. High-purity synthesis gas from electrolytic production. One of the major advantages of electrolysis-based hydrogen production is the high purity and lack of permanent catalyst poisons present in the gas stream. During the production of hydrogen from natural feedstocks such as coal or natural gas, significant quantities of sulfur are present that must be removed to avoid permanent deactivation of the catalyst. Sulfur is not the only element that acts as a poison towards the ion catalyst. Phosphorus, arsenic, and chlorine are also classified as permanent poisons. While carbon monoxide is not classified as a permanent catalyst poison, it poses a tremendous challenge upon designers. Synthesis gas from methane reforming contains trace amounts of carbon monoxide even after passing through the water-gas shift reactor, requiring an additional methanization reactor to remove these residual impurities. In China, where coal is a primary hydrogen feedstock for ammonia synthesis due to the lack of natural gas, short catalyst lifespan has been a common feature for many medium-size ammonia plants. If subjected to even trace concentrations of sulfur, the ion catalyst will rapidly deactivate. The beauty of electrolysis-based hydrogen production is that only one impurity is required for removal: oxygen. While oxygen is still a severe catalyst poison, it is classified as only a temporary poison, since it can be reduced by passing hydrogen through the catalyst bed. One must remember that all ammonia catalysts start off as an oxide of iron, which then undergoes a reduction process using hydrogen. During reduction, water vapor must be kept to a minimum to attain the proper crystal structure. Additionally, oxygen is highly electronegative and has an affinity for virtually every element, allowing straightforward capture and removal using ion particles, for example. The importance of improving reciprocating compressor technology. Synthesis gas compression, not kinetics or thermodynamics, limit the downscaling of conventional high-pressure ammonia synthesis. Ammonia synthesis stands out from other similar temperature catalytic processes, insofar as the operating pressure are many times greater than what is typically found in corresponding chemical production operations. This obviously means compressor design, maintenance, repair, and operation dominate the overall design criteria and parameters of an ammonia plant. Therefore, a significant improvement in compressor technology has great implications for improving the 100-year-old Haber-Bosch process. The reason for this is that larger plants make use of more compact, and thus lower cost and longer-lasting centrifugal multistage syngas compressors, while for smaller plants, these centrifugal compressors become too inefficient due to tip losses, turbulence-induced parasitic losses due to high Mach numbers, and the boundary layer effect. These respective phenomena arise due to the huge difference in the diameter of the impeller from downscaling from multi-thousand cubic meters per hour flow rates to a mere few tens of cubic meters per hour. No such centrifugal compressor option exists for these minuscule flow rates. Additionally, centrifugal compressors have a very low pressure rise per stage. This is exacerbated especially due to the low density of H2N2 mixtures at a 3:1 ratio, yielding a gas with a mean density of 0.37 kg per cubic meter. Since the operating principle of a centrifugal compressor is based on imparting kinetic energy into the gas medium, rather than squeezing it in a fixed volume chamber, this makes centrifugal compressors very sensitive to gas density, setting a clear limit to how light a gas can become before it can no longer be compressed. For example, pure hydrogen cannot be compressed without the addition of higher molar mass dilutant gases. Despite having lower footprints compared to reciprocating systems, centrifugal compressors still have relatively large footprints due to the multi-staging required to achieve pressures over 200 bar. Moreover, centrifugal compressors require very high RPMs to achieve a sufficient pressure rise. Therefore, operation with a cyclical power source is next to impossible, since only a slight drop in rotational velocity causes a much larger drop in the pressure ratio. Despite the lack of centrifugal compressor options for miniature production, present-day reciprocating compressors, as mentioned earlier, are no panacea either. For spasmodic renewable integration, they also face serious challenges. Traditional reciprocating compressors, either based on conventional or diaphragm architecture, suffer from high maintenance intensity. Diaphragm compressors, the backbone of high-purity gas compression, are not suitable for small-scale ammonia production. Diaphragm compressors feature a unique weakness that effectively outlaws their uses for intermittent ammonia production on a small scale. This problem is mainly imputable to their lack of reliability and longevity during cyclical operational regimes, despite their relatively good lifespan during steady-state operational regimes. Since distributed ammonia uses solar or wind energy, the plant must be able to operate at partial load capacity, with frequent startup and shutdowns required if the wind turbine or solar plant owner does not have a battery bank, which are expensive and short-lived. While we discussed this already, it is important to underscore and bears repeating. We cannot stress enough, it is not in any way the catalytic process, which is elegantly simple, but rather, the syngas compression systems, that penalize small-scale use. Diaphragm compressors suffer from premature diaphragm failure, attributable to sharp thermal gradients experienced when reaching operating temperature from static temperature. As mentioned earlier, the diaphragms are constructed from very thin smooth stainless steel discs, which flex only a small amount up and down driven by hydraulic oil. To minimize the risk of gas-oil cross-contamination, 3 discs are usually used simultaneously. While the disc is quite reliable during steady-state operation, it suffers from premature thermal-induced fatigue failures if cycled excessively. The hydrogen compression industry has experienced this issue for diaphragm units used for fuel cell vehicle fueling stations. This is one of the reasons fuel cells have failed to gain commercial momentum. Compressors operating in a frequent startup and shutdown regime can last as little as a few hundred hours before replacement of the diaphragm is required. During a regime of continuous use, 5,000 to 8,000 is possible, as aforementioned in the earlier section of the video. In light of this information, diaphragm compressors, regardless of their usage profile, suffer from an additional inherent weakness. Because the metal diaphragms are very thin to provide the elasticity required for a sufficient bending moment, the diaphragms are sensitive to particle erosion from the gas stream. If the feed gas consists of even the smallest solid particles, the diaphragm will be pitted and fail prematurely. Diaphragm life as a consequence is severely reduced above and beyond the already relatively poor life caused by thermal and fatigue stresses. This is even so in a continuous operational regime, such as with coal gasification, because filtration of micron-scale particles is very challenging. It requires no more evidence to conclude that this compression technology is simply not satisfactory for our requirements and will produce headaches for operators. Assuming the best-case particle-free gas stream and constant-state operation, since 5,000 hours is only 0.57 years of continuous operation, using classic diaphragm compressors would require a dedicated team to arrive at the site twice a year, undermining distributed production's improved automation potential. If the site is remote, this could add considerable transport costs. The task of replacing the diaphragm is a time-consuming and laborious process. Replacing the diaphragm requires the personnel to unbolt the diaphragm head, lift it either by hand, provided the compressor is relatively small, such as the current range of 100 to 300 ton per annum capacity. If over this capacity, a hoist is likely required due to the weight of the high-pressure rated head. Before the head can be removed, the crew must uninstall the hydraulic and gas fittings. Once the head is removed, they must then pull off the old discs and carefully reinsert the new diaphragm, and then bolt everything back together. This could easily take an entire day and cost thousands. The cost of the diaphragm itself is not necessarily the issue, but rather the labor and downtime that it imposes. What is called for is a steady-state operation which can endure all throughout the year with minimal degradation and maintenance requirements. For this to be satisfied, a new compression architecture is demanded. Small-scale ammonia production requires highly reliable near 24/7 operation with minimal human supervision. Downtime must be kept to a minimum. In order to achieve this, the major components need to be designed for utmost reliability. Since the reactor, purification system, and electrolyzer have effectively no moving parts, the compressor arises as by far the weakest link in the chain. Therefore, it emerges as the component most receptive to innovation and improvement, and it is where the bulk of engineering effort should be concentrated. It goes without saying that a better solution is required, or small-scale ammonia will fail to compete with centralized production that take advantage of low maintenance intensity and friction-free centrifugal compressors. One such solution is the metal hydride compressor, using hydrogen-occluding materials like lanthanum nickel alloys, abbreviated LANI5, which has a hydrogen storage capacity of as high as 6% by weight. Metal hydrides are an attractive option as it would entail the elimination of any moving parts other than a valve. Unfortunately, hydrides require temperature modulation for releasing the occluded hydrogen, and worst yet, at higher pressures, especially the pressures needed for ammonia synthesis, the hydrogen is hard to release from the metal. Most metal hydrides only readily liberate their occluded hydrogen at low pressures. Metal hydrides, although an elegant concept theoretically, are unlikely to be a competitive and viable solution. What is needed is a new and improved low-friction compression technology, of which without, small-scale production will flounder. At first glance, electrochemical hydrogen compression may seem as the obvious option, but the energy consumption and cost of electrochemical hydrogen compression is far too high to be competitive. The state-of-the-art electrochemical compression technology, while featuring outstanding compactness, and have a proven track record in niche hydrogen fueling stations, suffer from an energetic penalty, with the best-in-class modules using almost 7 kWh per kilogram H2 when compressing to 400 bar. In addition, the capex of these units is even higher than PEM fuel cells. These units cost over $5,000 per kilowatt, immediately ruling out their use. Their high cost is attributable to their use of expensive membrane electrode assemblies, MEA, which form the proton exchange membranes, made from expensive and specialized materials that do not adhere to our COTS methodology. In light of these failed compressor substitution options, there is still a highly promising solution on the horizon. We believe the solution is none other than liquid piston gas compression, using non-miscible ionic liquids. The major advantages of using an ionic liquid is eliminating all contamination of the synthesis gas, achieving superb tribological performance permitting nearly friction-free compression, and dramatically increasing TBO, and its attendant levelized capex. Ionic liquids also feature very low compressibility, reducing mechanical losses. In addition, most ionic liquids have high viscosity, enabling leak-free design using standard seals. They also have low corrosivity against stainless steel. An additional advantage of this compression technology is its drastically higher compactness, allowing even higher capacity miniature ammonia plants to be fitted inside the volume of the 20-foot ISO container. Ionic liquid piston compressors, thanks to the heat capacity of the working fluid, could achieve near isothermal compression, reaching close to 100% efficiency. Ionic compressors enjoy much longer operating intervals before scheduled maintenance, and this is where their performance shines for our needs. Their maintenance schedule profile according to Linde is in the order of 500 days, double that of aforementioned diaphragm compressors. This is attributable to their reduced number of moving parts, only around 8, versus over 500 in mechanical compressors. The ideal ionic liquid is immiscible with the gas, meaning that the ionic liquid will not end up in the synthesis gas and eventually in the reactor. Moreover, the ionic liquid does not possess a significant vapor pressure. In fact, the chosen ionic liquid has effectively zero vapor pressure. Linde Cryotechnik AG first invented the ionic compressor in 2001. With the patent already expired, it offers tremendous potential for commercialization in the ammonia production industry, as it's expected that China will eventually begin manufacturing this technology for the conventional compression markets to replace diaphragm systems. One of the principal reasons this technology has enjoyed little in the way of commercialization in surrounding industries is due to the fact that in the past 2 decades, the entirety of the intellectual property was held by Linde, making it difficult for competitors in the West to offer this technology without fearing patent infringement. This is quickly changing, however, since not only are the patents already expired, but there is increasing latitude for foreign manufacturers to offer slightly different designs while still using the principle of the ionic separator piston. There are claims online that China has recently begun developing its own ionic liquid compressors for hydrogen refueling. It is expected that this compressor technology will be highly disruptive if it lives up to Linde's stated performance. The Linde IC90 ionic liquid compressor designed for hydrogen refueling stations is 25 times more compact than a standard reciprocating compressor. A 900 bar, 370 cubic meters per hour, ionic liquid hydrogen compressor has a height of 1.1 meters, while a 100 cubic meters per hour, 440 bar reciprocating piston compressor has a height of 3.5 meters. Adjusting for pressure and mass flow, the improvement is nearly 30 times. There are parallels between this architecture and the diaphragm compressor, in that the hydraulic fluid provides the linear force required to compress the gas. The principal advantage of the ionic liquid design is the elimination of the failure-prone diaphragm disc, as well as its considerably higher volumetric flow capacity, even higher than traditional reciprocating compressors. This is due to two factors. Firstly, the elimination of the connecting rod, which allows on its own a much higher stroke-to-bore ratio. Secondly, this high stroke-to-bore ratio can be realized in a single compression stroke without excessive heat buildup, owing to the high heat capacity of the ionic liquid, which is able to absorb most if not all the heat generated. The elimination of the connecting rod and crankshaft not only reduces cost, it removes friction and life-limited components, and contributes to the compaction of the overall unit, since it removes the bulky crankcase and the necessary lubrication system, not to mention the need for oil changes. A standard radial hydraulic pump provides the compression energy, which is then driven by an electric motor. The Linde IC90 draws only 75 kilowatts to compress a mass flow of 370 cubic meters of hydrogen per hour, at an inlet pressure of 5 bar, pumping to over 900 bar. This means the ionic liquid compressor only consumes 0.5 kilowatt-hours per kilogram of hydrogen to reach nearly 1000 bar. The working principle of an ionic compressor is very straightforward. One can visualize the ionic liquid as a separation medium, substituting the metallic piston assembly. In the Linde design, invented by Robert Adler in the early 2000s, the mechanical force needed to push the ionic liquid to compress the gas derives from a conventional hydraulic fluid. The ionic liquid is not compressed with a hydraulic pump. Rather, a hydraulic piston beneath a layer of ionic liquid above it forces the entire assembly to move upward. In this case, the ionic liquid itself is not a working fluid per se, but merely a receptacle for the hydraulic fluid. It is akin to a separation medium to prevent contamination of the product gases, while also doubling up as a lubricant and coolant, both reducing friction and providing near isothermal operation, through the absorption of the thermal energy generated from the compressed gases, truly a versatile molecule. The ionic liquid can then be recirculated and cooled to maintain a constant temperature. Pachari Technologies has chosen a slightly different design from the original Linde architecture. Two separate chambers are present, one for a metal piston to displace the ionic liquid into the gas compression chamber. The metal piston in the ionic section is lubricated by the ionic liquid itself. Hydraulic fluid is not present to avoid contamination and mechanical losses from the hydraulic pump. It has been demonstrated that ionic liquid, especially those that are hydrophobic, the ones intended for use, possess extraordinary tribological properties, exceeding that of conventional mineral and synthetic oils. The key requirements for the ionic liquids are a low vapor pressure, a low solubility, and a high decomposition temperature. Some ionic liquids have decomposition temperatures as high as 400 degrees Celsius. Below is a discussion from a 2017 thesis on ionic liquids being considered as candidates for a Linde-style compression system. For lubricating well-known systems, such as steel-on-steel, as well as on difficult-to-lubricate systems, such as steel-on-aluminium, ionic liquid lubricants have been shown to outperform commercially available lubricants, such as fully formulated engine oil. Even without any additives, ionic liquids have shown remarkably better lubrication and anti-wear properties than normally used synthetic oils and are promising alternatives with considerably lower development costs. Furthermore, ionic liquids have superior durability as lubricants. Experiments have shown that ionic liquids even during long-term operation do not lose or change their properties. Therefore, from today's perspective, a change of ionic liquid must occur at the earliest after about 10,000 hours of operation, while conventional lubricating oils require an oil change after about 3,000 hours. The thesis commentary ends. The following text is from Containerized Technologies. As previously mentioned, ionic liquid-based liquid piston compressors have been successfully implemented for hydrogen fueling stations. This technology has the potential to spill over into the domain of Haber-Bosch technology to further process intensify, enabling the desired downscaling. Continuing to the thesis, a suitable ionic liquid is selected as the most reliable replacement for the solid piston in the conventional reciprocating compressors. Ionic liquids are room temperature salts that have very low vapor pressures. The ability to tune the physicochemical properties of ionic liquids by varying the cation-anion combinations is the feature of these liquids that make them as promising candidates to replace the solid piston. The ionic liquid, 1-ethyl-3-methylimidazolium bistrifluoromethylsulfonylamide, is recommended as the best candidate that can be safely used as a replacement for the solid piston in the conventional reciprocating compressors for compressing hydrogen in the hydrogen refueling stations. In addition, the corrosion behavior of various commercially available stainless steels and nickel-based alloys as possible construction materials for the components which are in direct contact with the selected ionic liquids is evaluated. The results show a very high corrosion resistance and high stability for all of the alloys tested in any of the 5 selected ionic liquids. The stainless steel alloy, AISI 316L, with a high corrosion resistance and the lowest cost, is selected as a material for all the components in direct contact with the ionic liquid, in the designed ionic liquid hydrogen compressor. This is the end of a portion of the thesis that deals with ionic liquid selection. Returning to Containerized Technologies. The authors tested numerous ionic liquids to find one with suitable compatibility with available stainless steel alloys. It was found that AISI 347 showed the highest corrosion resistance when exposed to each of the ionic liquids tested. The lowest corrosion observed was when using triacyltetraidsulfosphonium BIS, trifluoromethylsulfonyl, imide. It's interesting to find researchers working on Linde's largely proprietary technology. The authors appear not to be funded by Linde, suggesting the patent either has not been able to fully protect the basic concept of using ionic liquids as a compression medium, suggesting it is too broad a scope, or that Linde is beginning to promote the technology as to expand its market share. Either way, it's a perfect time to develop this novel compression system to replace diaphragm compressors in the high-purity gas industry, medical oxygen, argon, neon, semiconductor hydrogen, helium, etc. The authors of the ionic liquid selection thesis go on to say, quote, "So far, this technology has been limited to the monopoly of a single supplier," close quote. Only a handful of Linde ionic compressors are in operation today, since fuel cell vehicles appear not to be taking off anytime soon, and likely never will. Perhaps it will be micro-ammonia synthesis that will finally make this niche technology more mainstream, eventually causing it to spill over into more mainstream compression applications. As for why users of gas compression systems have not considered this attractive option cannot be answered. Perhaps it is due to industry conservatism, a lack of initiative, or the monopoly on the intellectual property. But what is clear is that ionic liquid compression is far more attractive than the traditional diaphragm architecture. The potential to reintroduce the Claude process via ionic liquid compression. Regardless of whether a mechanical or liquid piston is used, hydrogen compression work input is logarithmic as a function of pressure, meaning that compression energy demand is nonlinear, with decreasing amounts of energy required at higher pressures. This makes the use of medium-pressure alkaline electrolyzers very attractive, since the majority of the hydrogen compression energy is needed to go from atmospheric pressure to around 1 megapascal. For example, only 1.2 times more power is required to compress to 1000 bar versus 200 bar. If the hydrogen is already compressed to 50 bar in the electrolyzer, only 0.48 kWh per kilogram is required to reach 300 bar. This increases slightly to 0.65 kWh per kilogram if the electrolyzer pressure is reduced to 30 bar, a number that is very reasonable with the current maturity of alkaline technology. Thus, what can be inferred so far is that it is not the energy consumption of compression per se that is the limiting factor of downscaling. Rather, it's the chronically low reliability of extant low-speed reciprocating compressors that disincentivizes the miniaturization of production. Therefore, Containerized Technologies logically concludes the ideal avenue to approach downscaling is improving compression technology. The availability of much improved compression technology opens up another avenue of process intensification. When most people think of improving ammonia synthesis, they imagine some new catalyst or entirely new processes being invented, since, after all, this 100-year-old process is virtually exhausted. In the future, it may be possible to construct an ultra-high-pressure nearly single-pass plant using ionic liquid compressors. The equilibrium yield of ammonia at 400 degrees Celsius is close to 70% at 900 bar. The concept of ultra-high-pressure ammonia synthesis was originally developed by Georges Claude in 1917 in France. The principle was sound, since the equilibrium favored very high pressures at moderate temperatures. This was evident as Claude's reactor was far more compact than his medium-pressure peers, measured in tons per day per cubic meter of volume. The original Claude reactor operating at 1000 bar achieved 120 tons per day per cubic meter of reactor volume, compared to only 25 for the Haber-Bosch reactors of the time. Unfortunately, this higher density came at a cost, as the law of compensation almost always imposes. The major disadvantage of Claude's reactor was that it featured a significantly shorter catalyst life. While Haber-Bosch catalysts at the time lasted 2 years, Claude's lasted only 3 months. In addition, the alloys at the time were much weaker than ones currently available, requiring the reactor to be massively overbuilt, offsetting the cost saving from the smaller size vessel. General Electric invested in the Claude process in the 1930s and attempted to build a reactor, but experienced too many technical issues and eventually abandoned it. This sealed the fate of the Claude process. The downsides of the higher pressure system could simply not be circumvented by engineering, paving the way for the domination of the Haber-Bosch design. With newer, more stable and durable catalysts, higher strength alloys, and optimized compressor technologies, it may be possible to get close to these pressures while maintaining acceptable catalyst life. The trade-offs that must be made are between catalyst life, reactor compactness, pressure drop, and conversion per pass. When Claude was trying to achieve ultra-high pressure ammonia synthesis, compressor technology was much less capable than it is today. In fact, his plants in the 1920s were built to the absolute limit of the available compressors. Fast forward a century, and ionic liquid compressors may enable the resurrection of the long-forgotten Claude process, enabling miniature ammonia plants of even smaller footprints, even more so than the already relatively small footprints achievable with high-activity wustite. Considering the combination of logarithmic compression energy, the development of compact and high-pressure ionic compressors, and longer-lasting catalysts, the Claude design warrants serious consideration in the 21st century. We will now move on to briefly discussing common failure points on classic Haber-Bosch plants. Ammonia plant failures. G.P. Williams, from Allied Chemical Corporation, performed a detailed analysis on the nature of ammonia plant failures in a 1970s paper. During the 1975 to 1976 survey period, 45% of the downtime and 55% of the shutdowns were attributed to major equipment failures, with the synthesis gas compressor and primary reformer tubes, risers, and manifolds being the most troublesome major equipment items. The average downtime experienced in the ammonia industry is 16%. With major equipment failures and preventive maintenance accounting for 85 to 95% of the downtime. Primary reforming and major compressors and turbines are the leading contributors of major equipment downtime, accounting for 63% of the downtime. Compressor failures usually follow the following profiles. Severe vibrations on compressor and/or turbine, rotor failed, compressor thrust collar broke, coupling bolts failed, compressor seal failed, broken blades on turbine, reduction gear bearing failed, compressor O-ring failed, etc. The synthesis gas compressor leads the top 6 list, and it has the highest percentage, 25%, of the major equipment downtime ever attributed to a single major equipment item. The average ammonia plant had one shutdown due to the syngas compressor every 14 months during the 1971 to 1972 survey period, once every 12 months during the 1973 to 1974 period, and once every 9.5 months during the 1975 to 1976 period. Downtime days per shutdown averaged about 4. Syngas compressor problems are widespread, that is, 2/3 of the plants had at least one shutdown during the 1975 to 1976 period, with one plant reporting 10 shutdowns over the 2-year period. This sums up the downtime and failure profile of traditional ammonia plants. The above commentary is highly congruent with our claims, namely that dynamic components should naturally be expected to contribute most of the failures, leaving only the ultra-high temperature reformer tubes following. You may notice the commentary above makes no mention of primary NH3 synthesis systems failing. Since we have covered the key requirements of synthesis gas compression that makes the Haber-Bosch process unique among chemical production methods, we will cover the topics of reaction kinetics as determined by scale, and its design implications. The kinetics of the actual reaction, of which the most important is the rate-limiting step of nitrogen dissociation, is not affected by the gross volume of the catalyst. It is, however, strongly affected by the pore size of the active catalyst and its packing density. The second variable is often mistaken for kinetics. While heat transfer may strongly affect the reaction rate, for the most part in ammonia synthesis, heat transfer mainly determines how much leftover waste heat is produced along with the equilibrium temperature within the reactor. Heat transfer could be argued to be the only reaction variable affected by scale. Smaller reactors have higher surface-to-volume ratios, thus will produce less usable heat since they would radiate more heat into their surroundings. Approximately 1.5 kWh of thermal energy is released upon the formation of 1 kg of anhydrous ammonia, while only 0.45 kWh of heat is needed to heat and maintain 1 kg of synthesis gas to 500 degrees Celsius. This means the reaction is moderately exothermic and more heat is produced than is needed to maintain desired reaction temperature. In industrial-scale plants, this surplus of heat is harnessed to generate steam to cover most of the compression energy requirements. Obviously, unless insulated to compensate for the difference in the surface-to-volume ratio, smaller-scale reactors, depending on their exact size, would either purge more heat or merely slightly less than they produce, therefore leaving little to none left over to generate the steam to cover compression energy. For a miniature plant, the added hassle of installing a boiler and steam turbine makes such an option unattractive, and as with all turbomachinery, small scale results in abysmal efficiency, so a steam turbine would be useless. Therefore additional heat loss above mere reactor temperature maintenance is not a design consideration. Another important design variable is found in the design and optimization of gas separation heat exchangers. At 300 bar, ammonia must be cooled to around 26 degrees Celsius in order to bring the gas phase into the liquid state to permit separation. Once liquefaction is achieved, the ammonia is then removed and the unreacted gases go on to be reheated to the operating temperature. Smaller high-surface area high-heat transfer exchangers would be more compact and efficient than the large-diameter tubular heat exchanger installed on larger-scale plants, since they would perform their heat-exchanging function with greater rapidity, imputable to their higher surface-to-volume ratio and thinner wall thickness. This is a major advantage of a small-scale plant. The second variable is material usage. All else equal, a smaller reactor vessel will require marginally more material per unit mass volume of catalyst than a larger reactor. This difference in material usage is minimal and does not greatly affect plant economics. As mentioned earlier, existing ammonia plants make use of what's called a converter. The converter is often called the heart of the ammonia plant. It is essentially a large pressure vessel that contains the catalyst basket where the core reaction takes place. The basket is designed to permit the replacement of the catalyst without replacing the converter. The basket is housed inside the pressure vessel. It is constructed from stainless steel wire forming a solid container, made from wrapping metal cable into a mesh-like form. The converter features a removable cap that is bolted to the rim of the pressure vessel. This cap can be lifted by a crane exposing the catalyst basket for refurbishment or inspection. Many modern ammonia converters make use of active cooling, or what's termed a cold wall converter, where cold ammonia is flushed alongside the wall of the converter to maintain a temperature lower than the synthesis gas inside the catalyst basket. This serves to attenuate nitriding and high-temperature hydrogen, preserving the life of the reactor. For the miniature plant, the designer must choose between a cooled and non-cooled design. This ultimately boils down to the budget and specific requirements on plant longevity. Ammonia converters are designed to withstand the full pressure of the synthesis gas, up to 350 bar for conventional plants, but increasingly plants are using higher activity Wüstite catalysts, permitting a lowering of the pressure to 150 bar, to reduce compression energy expenditure. The state-of-the-art ammonia converters, such as the S200 tops, use SA542 grade B, class 4, a steel alloy with small amounts of vanadium and molybdenum alloyed for strength. This alloy is used for the converter wall construction, and while this is still a very high-strength alloy, ammonia converters are rarely made out of high-cost nickel and chromium alloys, such as Inconel. The ultimate tensile strength of ASME SA542, grade B, is approximately 860 MPa, while the yield strength is 585 MPa, but this strength falls considerably at its 450 to 500 Celsius operating temperature, while stainless steel or Inconel, thanks to its nickel content, retains most of its room temperature strength at 500 Celsius. Converter material selection is limited by nitriding and hydrogen attack. Nitriding is caused by atomic nitrogen diffusing into the metal. If the solubility limit is exceeded, which is around 6% for iron, precipitation of nitrate into the grain structure takes place. This can eventually cause structural failure in the form of cracks. Nitriding is a very gradual process, and the ensuing evidence of nitriding often occurs much later in the plant's life cycle. Nitriding is classified as a high-temperature corrosion process, taking place at temperatures greater than 370 degrees Celsius. Nitriding is considered an issue since ammonia synthesis operating temperatures almost always exceed this threshold. Nitriding causes the formation of a thin, heterogeneous, and brittle layer inside the reactor liner, any tubing, or metal exposed to hot ammonia. If nitriding continues unabated, the nitriding layer will grow until entire metallic sections become brittle to the point of failure. Nitriding rarely exceeds a few fractions of a mil per year in the innards of the converter. The solubility of 3O for stainless steel is 12% by mass at 530 degrees Celsius, meaning that nitriding will occur once this limit is exceeded if nitriding propitious conditions are present. Thankfully for ammonia plant designers, nitriding need not be overly concerning, since the ammonia reaction rate is so low, only at best 18 to 20% of the ammonia is converted per pass. This low concentration of ammonia keeps the nitriding rate to acceptable and manageable levels. Nitriding becomes a serious issue when NH3 concentrations exceed 50%. This may place limits on the resurrection of the Claude process unless higher nickel fraction alloys can be used. The cost of converter construction is substantial for large-scale plants, as the manufacturing technology required to fabricate a multi-thousand-ton-per-day cylinder is considerably more elaborate and costly than what is required for the miniaturized plant. For large-scale plants, compared to the total annual output of ammonia, the material usage and intensity is relatively small as a ratio of high-end alloys per ton of annual ammonia produced. For illustrative purposes, we calculated the mass and volume of a typical large-scale ammonia converter using a patent drawing, which was used to surmise wall thickness. The weight versus catalyst volume of benchmark ammonia converters is estimated using three-dimensional CAD modeling of a 2D image. To confirm the veracity of the inferred 3D estimation, we compare to an ATB Riva Calzoni reactor, whose dimensions and weight were published. For the inferred 3D reactor, the catalyst volume is 30 cubic meters, and the dead weight of the reactor is 252,000 kilograms. Assuming an alloy price of $1,500 per ton, we arrive at $378,000 for material costs alone. Fabrication is difficult to estimate as no literature to date has been published on ammonia converter fabrication costs. We estimate a conservative material fraction of 25%, yielding $1,512,000 for the converter, but the real number is most likely substantially higher, since most converters are manufactured by Western firms in high labor rate countries. The cost of transport and erection are very high for such heavy converters, which require a high-capacity crawler crane for erection. The catalyst cost is $1,215,000, assuming $15 per kilogram for bulk orders. The cost estimate for the SA542 steel is conservative, with estimates from Alibaba ranging from $600 to $1,200 per ton. Assuming a lower-end catalyst productivity of 0.26 kg NH3 for a lower pressure plant, data from Capsum Industrial, the reactor produces 20 tons per hour, or 176,000 tons per year. The reactor capex is thus only $15.35 per ton per year in the first year. Since the converter is the single biggest and thus expensive item in the ammonia plant, and yet the material plus fabrication cost is quite minimal, this confirms the high cost of on-site labor, site preparation, and assembly erection, as preponderating the cost of site-built plants. Permits, land acquisition, utility hookup, insurance, regulatory hurdles, zoning, and various other ancillary factors contribute a large portion of the capex of chemical plants. Note that land costs can be dramatically reduced for containerized plants since stacking is possible up to many stories high, if production in urban areas is desired, and land which is not specifically zoned for chemical production or industrial use can be used. For example, a 20-foot ISO ammonia container can be installed in a residential backyard, since the ammonia plant is contained within a fireproof container, keeping the plant from becoming an eyesore. Let's now compare the mass-catalyst ratio for a reactor sized for 40 kg NH3 per hour. For a 40 kg per hour reactor, with a catalyst activity of 1 kg NH3 per kilogram of catalyst per hour, the diameter is reduced to 0.38 meters, with a mass of 252 kilograms and a catalyst volume of 0.03 cubic meters. Note the mass-to-volume ratio remains constant as a function of scaling. The only scaling variable that is subject to nonlinear modification is the surface-to-volume ratio, caused by the square-cube law. Data from a book on high-temperature corrosion of metals, the nitriding rates are plotted for various componentry of typical TOPS-style ammonia converters. The highest nitriding rate is found in the lining of the main converter vessel, with a corrosion rate of 9.8 mils per year. The lowest corrosion rate is found in the wire meshes and inner shell, where a nitriding rate of 0.04 and 0.4 mils per year is experienced. These figures are taken from the book, High Temperature Corrosion and Materials Applications, by George Lai. Among the alloys, the lowest nitriding rate is found for Inconel alloy 804, comprised of 50.4% nickel, alloy 804 nitrides at only 1.2 mils at 76 megapascals, while stainless steel 310 nitrides at 8 mils per year. But this pressure is nearly twice what is typically found in Haber-Bosch plants, so this number is not representative of the typical nitriding rate found in industrial ammonia plants. Pure nickel experiences virtually no nitriding and could be used if the price permitted. For an operating pressure of 354 bar, stainless steel 310 experiences 0.14 mils per year, 314 at 0.10, 309 at 0.23, 321 at 0.37, 316 at 0.47, 304 at 0.59, 302B at 0.73, 446 at 1.12 and 430 at 0.90. Stainless steel 330 with 0.47% silicon content experiences a much lower nitriding rate at only 0.06 mils per year, and stainless steel 330 with a 1% silicon content features an even lower nitriding rate at only 0.02 mils per year. Early ammonia converters, material challenges. Early ammonia synthesis converters made by BASF, constructed out of carbon steel during the 1910s, experienced catastrophic failures induced by high-temperature hydrogen attack. Failures were so common that engineers had to place the reactor vessels in concrete bombs or explosion-proof chambers to prevent damage to surrounding equipment or harm to personnel. It was only after Carl Bosch made use of chromium steel that the process could be commercialized. Increased resistance to hydrogen attack is realized by adding chromium, tungsten, molybdenum, or vanadium to the steel, either by themselves or in combination. A vanadium concentration above 1% does not markedly improve hydrogen resistance, but increasing chromium content does not show this diminishing return until around 2%. With 2% or more chromium, the rate of hydrogen decarburization and nitriding is severely retarded, and is confined to the area near the surface. Ferrous alloys tested by Vanik containing 7.7% chromium performed only marginally better than at 2%. In the paper, Hydrogen Attack on Metals at High Temperatures and Pressures. Corrosion and Material Protect, by J. Schutten, 1947. ASTM A387, Grade 11, UNS number K11789, is a low-carbon, 1.25 chromium, 0.5 molybdenum steel. This alloy was found to be highly resistant to hydrogen attack under the most severe conditions encountered in NH3 synthesis, and variants of this alloy have been to date. A seminal text in the history of ammonia technology was published by the National Bureau of Standards in 1927, by J. S. Vanik, titled, Deterioration of Steels in the Synthesis of Ammonia. The authors tested a great number of alloys and established that vanadium and chromium were the most effective at halting severe material degradation. The proper alloying serves to form an outside protective layer, as most corrosion-resistant metals do, preventing hydrogen and nitrogen from inflicting further damage to the interior of the material. Material science has made great strides since the days of Carl Bosch. The modern designer now has entire catalogues of alloys to choose from. The scary aspect of running very hot and high-temperature hydrogen gas need not dissuade the designer. With proper material selection, this material compatibility challenge can be ironed out, pun intended. Ammonia is by no means the only engineering sector that is forced to handle undesirable pressures due to fundamental chemistry requirements. The fuel cell industry, water jet cutting industry, the LDPE, low-density polyethylene synthesis industry, which operates at 350 degrees Celsius at up to 50,000 psi, and the synthetic diamond synthesis industry, all have to deal with pressures in excess of 1,000 bars. These sectors have all learned to deal with very high pressures through scrupulous engineering, designing with material fatigue, corrosion, and stress constraints as core design criteria, which has forced designers to make the best use of finite element analysis, active monitoring of the material through stress and strain gauges, and periodic inspection. The designer of the small-scale ammonia plant need only to design his components to handle 20 to 30 megapascal, which in the grand scheme of things, is not the worst of high-pressure engineering. Hydrogen embrittlement, chemical and atomic. Hydrogen-induced embrittlement can be classified into two categories: chemical and non-chemical. Non-chemical hydrogen embrittlement is what usually comes to mind. This is a low-temperature phenomenon where atomic hydrogen diffuses into the crystalline lattice, engendering a perturbation of the grain structure, ultimately leading to detrimental effects on its strength. The second mechanism is chemical, whereby sufficiently high temperature can cause chemical reactions between the carbon in the alloy and the surrounding hydrogen gas. Hydrogen will not form chemical reactions with pure iron, so in very low-carbon ferrous metals, there is insufficient carbon to react with. Non-chemical hydrogen embrittlement is typically not the mechanism that is referred to when discussing hydrogen-induced material failure experienced in ammonia vessels. Rather, chemical embrittlement, usually called high-temperature hydrogen attack, abbreviated HTHA, which takes place above 400 degrees Celsius, often the two mechanisms are confused. Non-chemical hydrogen embrittlement does not occur above 150 degrees Celsius, since the velocity or mobility of the hydrogen atoms is too high for sufficient concentration to occur. Most metals are immune to atomic hydrogen diffusion at above this threshold, so this form of hydrogen-induced corrosion need not be a concern for the ammonia plant designer. Another form of low-temperature hydrogen-induced embrittlement is what's called hydrogen-induced cold cracking. This occurs over weld zones in ferritic steels, but like classical embrittlement, it only occurs at below 100 degrees Celsius. Embrittlement will usually begin at the site of a crack, notch, or corner, or in any site with high multiaxial stress. Because these sites have high inter-atomic distance, they are conducive to hydrogen penetration. The hydrogen begins to permeate, and enlarges these sites until they reach their critical fracture stress. Most carbon-containing steel alloys can handle hydrogen at lower temperatures up to pressures as high as 2000 bar, without experiencing severe embrittlement. Once this pressure threshold is reached, non-chemical embrittlement becomes a severe issue. The rate of diffusion of hydrogen varies as the square root of the pressure. Austenitic stainless steel and beryllium copper are especially resistant to hydrogen embrittlement at low temperatures. The American Petroleum Institute publishes the Nelson curve, which helps designers choose appropriate materials depending on the temperature, pressure, and hydrogen concentration. For high-temperature hydrogen attack, which is the principal concern for material selection in ammonia plants, chromium-nickel alloys, due to their absence of carbon, perform spectacularly. From a paper on hydrogen attack, quote, HTHA is not considered in the case of austenitic stainless steels due to the absence of carbides. In these steels, carbon content is very low and solubility of carbon is very high. Moreover, heat treatment consists of hyperquenching to solubilize carbon and then avoid the formation of carbides. As no carbides exist in these alloys, HTHA is not relevant, close quote. From the paper, Hydrogen-induced disbonding and embrittlement of steels used in petrochemical refining, by S. Pillet and L. Coudres, published in Gaseous Hydrogen Embrittlement of Materials in Energy Technologies, The Problem, Its Characterization and Effects on Particular Alloy Classes, 2012. Chemical embrittlement or high-temperature hydrogen attack in carbon steel is caused by a mechanism where atomic hydrogen penetrates into the carbon steel, forming internal methane pockets. Hydrogen initially reacts with carbides present in the steel, such as cementine and martensite. Once the atomic hydrogen reacts with the carbide, it eventually forms into methane, which due to its low density, expands and cracks the metal. The internal methane pockets cause the formation of fissures and microcracks, eventually compromising the structural integrity of the material by inducing internal grain boundary separation. Welded regions are more prone to hydrogen attack, as welding causes the formation of carbides, leading to a more carbide-dense section, attractive to the hot hydrogen. High-temperature attack is effectively a process of decarburization, where carbon leaves the ion-containing compound and is picked up by the hydrogen. Hydrogen-induced material weakening, regardless of the mechanism, is potentially a concern mainly because most metals are somewhat hydrogen-occluding. The small size of the hydrogen atom makes it inevitable that a certain amount of it will eventually penetrate deep into the material, especially at high pressures. The Tesoro-Anacortes refinery explosion in 2011 was caused by high-temperature hydrogen attack weakening the heat exchanger wall housing steel, causing it to rupture. To this date, ammonia converters failing in a catastrophic manner imputable to hydrogen attack has been documented only once, while for nitriding-induced embrittlement, no case has been documented. This illustrates the success of materials selection and the safety factors employed in choosing the appropriate wall thickness, despite the immensely harsh and antagonistic conditions experienced during ammonia synthesis. In 2006, the Mosaic Faustina ammonia plant in St. James, Louisiana, experienced a catastrophic failure in the synthesis loop boiler feed water heater, causing the separation of the inlet channel from the heat exchanger housing. Upon forensic examination, the failure was traced to hydrogen-induced cracking. Since the early experiences at BASF, carbon steel was abandoned as a structural material in favor of ultra-low carbon alloy steels. Many early reactors made use of a design where the load-bearing pressure vessel walls made use of low-carbon steel, but a carbon steel layer was placed on the inside, to bear the brunt of the hydrogen attack and decarburization. A novel design in the future may be the use of a ceramic liner on the insides of the reactor wall and heat exchanger tubes, shielding the ferrous material from the hot reactant products. With the availability of modern low-carbon nickel-chromium alloys, hydrogen attack becomes less of a concern than during the initial development stage. Material usage and component selection. One of the principal justifications for scaling is the nonlinear relationship between capacity and capital expenditure. In the beginning of the video, we mentioned that the scaling factor for ammonia plants is estimated to be 0.64, meaning that if the capacity of the plant doubles, the capital costs only increase 64%. This is the principal impetus driving the ever-growing scale of Haber-Bosch synthesis. But is this necessarily always the case? Upon closer examination, this law is not inexorable nor much of a law at all. The primary cost contributor is the cost of the material and concomitant fabrication of these materials into components. The cost of the material is a largely fixed cost, that is, it has little to no elasticity, larger purchase volume does not affect the price of nickel or iron, for example. But obviously, the cost of fabrication and production is a variable cost, and greatly so, which is largely influenced by the volume and speed at which the production facility churns out a particular part or component. The speed at which a component is fabricated has the second largest influence on the cost after its raw material acquisition. For example, if a part has to be machined with a 5-axis CNC machine, and the machine sells for $90,000, has a useful life of 20,000 hours, and costs $50 per hour to operate, if the part requires only 1 hour to machine, the machine can produce a part for $55. If the same machine required 8 hours, on the other hand, the cost of the part would increase to $440, even if the cost of the metal itself remains the same. Interestingly, because of the small size of the plant, the major components that require machining can be produced rapidly and at very high volumes. It bears repeating that the dogma of bigger equals better is entirely overturned here, since small components translate into much easier manufacturing, and the potential to tap into vast supplies of mass-produced components. Since a small ammonia plant does not require a high flow volume, unlike large-scale plants which use flanged connections, small-scale units would make use of mainly small threaded fittings, rated for high pressure and constructed entirely from 304, 310, or 316 stainless steels, and machined with 4-axis vertical machining centers. If purchased from retailers such as Grainger Industrial Supply or Mastercar, the price of all these individual components would still only amount to a few tens of thousands for a 100 to 300 ton per annum plant. On the other hand, if these fittings are bought in bulk from industrial suppliers in China such as Siluoke Fluid Equipment Inc. and Zhejiang Fangdun Instrument Valve Co. Limited, the price would amount to below $5,000 for a 100-ton class plant. The number of suppliers who specialize in mass-producing ultra-high-pressure fittings and valves that find application in a number of fluid transfer industries is great in number. Most of these components can be procured for very competitive prices on Alibaba.com, and shipped anywhere in the world by container, or if not too heavy, by air freight, which presently due to the continued reverberations of COVID is about $8 to 10 kg for Hong Kong to San Francisco. It makes no sense whatsoever to custom fabricate fancy components when these high-pressure stainless components can be readily used in low-flow rate plants. For a small reactor weighing only 1/4 of a ton, more expensive alloys such as stainless steel or even Inconel can be used, without much of a concern for cost, as the relative contribution of reactor mass is trivial. The use of these high-nickel chromium alloys allows the plant to be used in corrosive environments, although this should not be a concern since the sensitive components can be hermetically sealed from the elements in the ISO container. For large-scale plants, the volume may be less important than the conversion rate per loop, hence the choice to operate at lower space velocities. For small-scale plants, however, what is desired is maximal footprint reduction, hence the choice to increase space velocity at the expense of conversion and pressure drop. The higher converter material loading is tolerated as a necessary design compromise that is unavoidable by downscaling. The additional material loading from downscaling pales in comparison to the total system capex, principally dominated by the prime mover, namely the electrolyzer, solar farm, or wind farm. Space velocities and the factors that determines of their selection. For industrial scale plants, space velocity is largely a function of the pressure. The common space velocity of a low-pressure loop is set at 5,000 to 10,000 hours, a medium-pressure loop at 15,000 to 30,000 hours, and a high-pressure loop as high as 60,000 hours. For our smaller-scale plant, we have chosen moderate to high pressures, thus reasonably high space velocity, bearing a high catalyst productivity. One of the principal advantages of higher pressure systems, namely 30 megapascals or more, is the ability to more easily separate the synthesis gas through condensing the reacted product. A higher pressure is almost always salutary to the process, but the same cannot always be said of a high space velocity, since high space velocities induce a greater pressure loss. Higher pressure itself does contribute to pressure loss, as the reactant gases can penetrate further into the porous catalyst, but by far the greatest determinant of pressure drop is space velocity, which itself is the single biggest factor affecting yield after pressure. It was found using data from the high-activity Wostite catalyst that there was little need to increase the power density through process intensification of the reactor. The ancillary componentry should therefore be the main target of efforts to process intensify. Moreover, even if there was a need to process intensify, there is little ability to actually do this outside of improving the auxiliary systems, which themselves occupy the most space as the reactor vessel, chilling, and reheating exchanger, are relatively compact. Since compressor capex, footprint, and opex is a major limiting factor, by using ionic liquid compressors, we allow the plant to raise pressure while keeping compressor footprint low, enabling a raising of the reactor output. Hence, there exists a compromise between compressor footprint and reactor footprint. Ionic liquid compression thus plays a central role in permitting the process intensification and consequent miniaturization of the ammonia plant. For example, a 40 kg per hour ammonia plant would use only 6.9 liters of catalyst at a high space velocity of 40,000 hours. What can be concluded from this inquisition into the downscaling ammonia synthesis technology is that reaction kinetics remain unaffected, while increased thermal transfer does not impose major design considerations, other than minor reactor insulation. What is highlighted is that it is not kinetics, but rather compression and economic factors, that remains as the obstacle and explains the preference to build ever larger plants. It is therefore paramount to focus much of the research and development efforts on compression technology, rather than squandering time on futile catalyst pursuits which have a long history of yielding little to no value. Over 100,000 different material combinations have been evaluated as ammonia synthesis catalysts. None have proven sufficiently superior to iron to pose as a possible contender to replace it. The odds of discovering a new and improved catalyst which greatly outperforms iron are slim to none, as nearly every conceivable elemental combination of the periodic table has been tried or at least simulated. In spite of this, there is a small chance that one such elemental combination may prove marginally more effective than iron. Only cobalt and molybdenum bimetallic nitrides could be possible contenders to replace iron. In 2001, Jens Kain-Reskoff predicted that cobalt and molybdenum bimetallic catalysts could attain high activity for ammonia synthesis, due to their excessively high and low nitrogen binding energies. Molybdenum binds nitrogen very strongly, while cobalt binds it very weakly. Combining the two proves to yield an effective catalyst in theory, but real-world tests demonstrate only marginal improvements, and most bimetallic nitride catalyst experiments experienced low stability and rapid deactivation. The reason for the theoretically high activity of the cobalt-molybdenum combination is that we want a high absorption energy for performing nitrogen dissociation. When N2 is bound to the catalyst surface, it breaks the bond, forming atomic nitrogen. But when ammonia is formed, it is desired to have a certain percentage of catalyst sites producing only weak nitrogen absorption, with a low surface coverage for atomic nitrogen. A cobalt-molybdenum bimetallic alloy could in theory achieve activities as high as ruthenium, which is around 2 to 4 times higher than iron at lower pressures. But the issue is the cost of such a catalyst could possibly offset the reduced reactor volume and catalyst mass, making it redundant. For decomposition, the reverse of synthesis, it's been demonstrated that Cantor alloys, also called high-entropy alloys, based on cobalt-molybdenum nanoparticles, achieve decomposition turnover frequency 20 times higher than straight metallic ruthenium. But one cannot compare and extrapolate synthesis and dissociation in a simplistic framework of reversing the catalysts in order. For example, ruthenium is 10 times more active than the second most active catalyst for decomposition, nickel, while iron has very low activity, but ruthenium is only 4 times more active than its second best, iron, while nickel has a very low activity if not zero for synthesis. The mass reaction rate, Rm, of ruthenium catalyst is higher by 3.9 times and the TOF, turnover frequency, is higher by about 3.4 times than that of Wostite. For ammonia decomposition, the catalytic activity is as follows. Ruthenium, rhenium, nickel, cobalt, iridium, iron, platinum, chromium, palladium, copper, and lead. From McCullough and Chiang 2020. For ammonia synthesis, the elemental distribution looks very different. The activity for synthesis is as follows: iron, osmium, uranium, molybdenum, ruthenium, manganese, and cesium. For synthesis, nickel has the lowest activity, followed by cobalt, from Huazhong Liu, 2013. Ramboa and Jorti studied the activity of pure osmium powder, comparing the activity with Fe and Ru. They found the activity of osmium was 100 times higher than iron at 200 degrees Celsius, but 100 times lower than ruthenium at the same temperature. If the temperature is raised to 400 degrees Celsius, the activities reverse, and iron is marginally more active than ruthenium, and 100-fold more active than osmium. What can be deduced from this is that ammonia kinetics are highly thermally dependent, with the same elements exhibiting dramatically altered performance at different temperatures. This is the main reason the huge efforts by catalyst researchers to find a low-temperature catalyst has yielded such poor results. One must remember that ammonia synthesis is a reversible reaction. Since we know decomposition favors low pressure and high temperature, we can assume low temperature synthesis would be ideal. But the reality is the reaction is extremely slow at low temperatures, despite theoretical yields being very high, so designers were forced to increase temperature to speed up the kinetics, but once this is done, a precarious situation is reached. If pressure is lowered, a dramatic loss of activity is experienced, as we are now essentially decomposing the freshly formed ammonia, reaching a zero-sum process, where decomposition outstrips synthesis. It thus be said that high pressure is simply used to prevent decomposition. We want the high temperature that favors decomposition, but we must prevent this from occurring, so the pressure is used to cancel the tendency for decomposition. Therefore, high pressure will never be overcome unless entirely new mechanisms are discovered, such as plasma synthesis, but plasma is highly tentative and the results so far are extremely disappointing. What can be observed is that many of the most active elements for decomposition do not show any activity for synthesis, and vice versa. Iron is 20 cents per kilogram, while molybdenum is $30 per kilogram, and cobalt is $79, with an average of $54 per kilogram, yielding a 272-time price difference for the raw material alone, not including catalyst processing and deposition costs. In conclusion, alternative catalysts will require much higher activities than currently found to justify their higher costs. Early ammonia synthesis catalysts were based on magnetite, reduced with hydrogen after melting with alkali promoters to produce the desired iron crystal structure. The new generation of iron catalyst, while nearly identical in overall form, made use of the slightly different wustite crystal structure. What's remarkable is the ammonia synthesis catalyst is considered the most durable catalyst among all industrial catalysts, showing virtually no structural and morphological changes after 20 years of extreme conditions of pressure and temperature. As long as the catalyst is not exposed to oxygen, a severe poison, with less than 0.5 ppm O2, reducing activity by as much as 25%, due to the formation of iron oxide. The wustite or magnetite-based catalyst is highly durable, active, and cheap, making its substitution and replacement a very tall order indeed. In classic plants, oxygen removal is typically done after the methanization step using a copper ammonium salt. For small-scale plants, a plethora of oxygen removal options are available. One such option is a replaceable iron-based oxygen scavenger. The complete oxidation of 1 gram of iron can remove 300 cubic centimeters of oxygen in standard conditions. The PSA generator produces a purity of 99.999%, with up to 99.9995% being achievable at lower flow rates using the carbon molecular sieve. The remaining 5 to 10 ppm is removed using an oxygen absorber. More on iron ammonia synthesis catalysts. In the 1980s, Huazhong Liu and other Chinese researchers discovered a new high-activity ammonia synthesis catalyst based on wustite as a precursor in place of magnetite, the oxidic promoters being substantially the same. It was shown that the reaction rate of the new catalyst is 30 to 90% higher than that of the traditional one, and that such an activity difference increases when temperature decreases, as occurs with ruthenium. Resistance to sintering and mechanical strength are reported to be the same as the traditional catalyst, while resistance to carbon monoxide impurities is higher. The overall ammonia productivity increased significantly. For example, A figure quoted from older magnetite catalysts from the 1960s shows 19.6% conversion at a gas-hourly space velocity of 29,000, while the Chinese wostite catalyst demonstrates conversion of up to 33% at a space velocity of 30,000, at a pressure of 30 megapascals. The wostite-based catalysts exhibit about 60% higher catalytic activity than promoted magnetite on average. As of today, it is considered the most advanced commercial iron catalyst with the highest activity and lowest production cost in the world. It is more than competitive with ruthenium-based catalysts, which so far have been handicapped by the rarity of ruthenium as an element, with only 5,000 tons of available reserves, lending a prohibitive market price of $16,000 per kilogram. The Chinese catalyst was licensed to German and Swiss companies and is marketed in the West as Ammo Max 10 by Clariant. China continues to dominate wostite-based ammonia synthesis catalyst manufacturing. Shaixing Shunyu Catalyst Co. Ltd. is the leading manufacturer of the A301, A110-2, and the A5 series catalysts. The use of the higher activity wostite usually encourages industrial operators to reduce operating pressure. In fact, some plants using the wostite-based catalyst in China run at only 15 megapascals. In our case, we want footprint reduction, so the pressure is most likely going to be kept at above 20 megapascals, while space velocities are kept commensurate with this pressure. Virtually all ammonia synthesis catalysts are doubly promoted with alkali metals, but aluminum oxide is also used. Donors can be classified into two categories: structural donors and electron donors. In the case of ammonia synthesis, potassium performs the function of an electron donor, donating electrons to the iron, facilitating the breakage of the diatomic nitrogen bond. Calcium serves as a structural promoter, blocking certain catalyst sites and exposing more active sites, what is termed 110, 111, referring to the morphology of the crystal structure and its number of faces. Site 111 is thought to be over 500 times more active than Site 110. The calcium structural promoter can increase the number of highly active sites over the less active ones. This is achieved by fine-tuning the concentration of the promoter. The alkali promoters are nearly always present as an oxide, such as potassium 2 oxide or calcium oxide. Promoters not only accelerate the turnover frequency, TOF, but they also serve to extend the active life of the catalyst, as without promoters, magnetite-based catalysts rapidly deactivate. For wostite, the highest activity is found when the Fe2+ and Fe3+ ratio is 6. At this ratio, the reaction rate or turnover frequency, TOF, is 95 millimoles per gram of catalyst per hour, or roughly 1.618 kilograms NH3 per kilogram of catalyst per hour, at 15 megapascals and at an intermediate space velocity of 30,000 hours. If the pressure is doubled, the activity would increase to over 3 kg NH3 per kilogram catalyst. In a paper by Anders Nielsen of the Halder Tops Research Laboratory in 1953, he plotted the activity of a traditional magnetite catalyst versus the gas-hourly space velocity at 33 megapascals and 450 degrees Celsius. At 330 bar, the activity of the old magnetite catalyst is only 0.98 kilograms of NH3 per kilogram catalyst per hour, at a 30,000 space velocity. From the same Nielsen chart, when the space velocity is increased to 43,500 hours, the activity nearly doubles to 1.82 kilograms per kilogram hour, while the conversion per pass barely decreases from 19.6 to 19.0%. If higher pressure drop is tolerated, the designer could bump up the space velocity to 70,000, and bring his yield all the way up to 2.6 kilograms NH3 per kilogram catalyst, while conversion drops by only 2.5% to 16.5%, from 19%. In light of this information, the designer is left with the choice to make a trade-off between catalyst yield, longevity, reactor volume, and compressor size. For small-scale plants, it may seem at first glance that a more moderate pressure is desirable from the perspective of component sourcing, since the cost of high-pressure rated components is proportional to their mass, which is then directly linearly proportional to the pressure they must withstand. On the other hand, these higher pressures permit a considerable reduction in the scale of the components, since less catalyst is needed, reducing the material required even though thicker walls are needed. A fine balance between these two variables must be struck. The principal advantage of lowering the pressure is minimizing nitriding as well as maximizing the catalyst longevity. Pressure drop is an important design consideration due to the phenomenon of intraparticle diffusion. Pressure drop is a design concern due to the requirement to repressurize the feed gases during each loop, consuming additional power. Pressure drop is a direct function of the void volume of the catalyst particle. Large particles feature higher void volumes permitting higher diffusion, especially at higher pressures. Thus, smaller particles dramatically reduce gas diffusion and hence pressure drop. It was found that particles less than 0.9 mm effectively eliminates intraparticle diffusion. Spherical-shaped particles are ideal. They minimize both pressure drop as well as maximize activity. Smaller particles also possess much higher activities than larger particles. For example, for particles 0.6 to 1.2 mm in diameter, the relative TOF is 300, while it drops to 61 for a particle size of 6 to 9 mm. The durability of the wustite catalyst was found to be significantly improved over the magnetite-based ones. The attrition rate for magnetite was 1.5% over 6.5 years, while it was only 0.5% for wustite. If the traditional magnetite has a TOF of 4.8 kg NH3 per liter of catalyst, at a space velocity of 40,000 with 19% conversion, we can assume this can be increased to 6.3 kg per liter of catalyst per hour, assuming a conservative 30% increase in activity. This means, for example, a hypothetical 40 kg per hour plant would require only 7 liters of catalyst volume, the size of 14 small handheld water bottles for reference. Purification of feed gases. We have discussed extensively the compression, catalyst, and thermal challenges encountered in ammonia synthesis, especially as it pertains to downscaling. We have yet to mention the need for gas purification outside of oxygen removal. Using electrolysis, only one impurity must be dealt with, oxygen, and this element is quite easy to remove. But with coal, natural gas, or municipal solid waste-based hydrogen sources, impurities, especially permanent poisons, such as sulfur, become a much greater challenge. In fact, the biggest challenge encountered by the designers of early ammonia plants was not making sure the high-pressure converter didn't blow up, but rather, producing a constant stream of ultra-high purity hydrogen gas from the very dirty coal sources that were available in 1920s Germany. Extensive scrubbing, washing, pressure swing absorption, and zeolite absorption are required for these dirty sources. While ammonia catalysts do not require purities lower than the mid to high part per billion range, absorbent technologies that offer part per trillion range are commercially available, and will significantly improve catalyst yield and lifespan. This is yet another reason why small-scale plants are so desirable, as off-the-shelf absorbent cartridges that are readily bolted into place and changed out when needed can be easily used for low-flow rate plants, obviating the need for complicated scrubbing and purification systems, commonly used on mass-scale plants. Methanization and water-gas shift reaction can remove impurities down to the high ppm levels. The relatively pure gas can then be purified down to parts per trillion levels, using specialized absorbents such as Integris Megator and Gatekeeper, which use micron-size membranes. The lifetime of the Megator membranes is around 1 year of continuous use, depending on inlet impurity concentrations. These high-purity filters are not membrane filters that rely on differential molecular size, rather they employ specialized substrates that facilitate physicochemical bonding between the gas impurities targeted for removal. Another filtration technology are metal-organic frameworks. The VC-Matronics purifier can reduce O2, CO2, CO, H2O, sulfur compounds, and non-methane hydrocarbons from 50 parts per million down to less than 1 part per billion. Water vapor purification works via physioption, using zeolites such as clinoptilolite, chabazite, mordanite, and erionite. To remove oxygen, carbon monoxide, and carbon dioxide, reduced metal powder is dispersed inside the zeolite-containing cartridge. Zeolites are an aluminosilicate compound widely used for their physisorption properties. Their cost is surprisingly low, with small diameter zeolite sieves selling for $150 to $200 per ton in bulk. The ammonia industry is not unique in requiring high-purity gases. Many modern technologies that are taken for granted could not be realized without ultra-high-purity gases. This is especially so in the semiconductor manufacturing sector, which requires ultra-high-purity hydrogen, ideally in the parts per trillion range, which cannot even be achieved by cryogenic distillation. Semiconductor photolithography, epitaxy crystal growing, dry etching, and gas chromatography, among many others, required part per trillion purity gases. Many users of these high-purity gases make use of cartridge-type in-line filters to achieve the required purity, rather than procure the gas in bottles already purified, which is often far more expensive. Users of these high-purity gases can buy gas bottles commercially and have them refilled and simply purchase purification cartridges and replace them when needed. For non-metal organic framework cartridges, namely those that merely use standard zeolites, they can be simply refilled with fresh zeolite when saturated. Gas purification is the sine qua non for ammonia synthesis, of which without, the process would be impossible as the catalyst would deactivate within mere minutes of use and be rendered into a state beyond salvation. While we discussed in detail the possibility of using coal, natural gas, and solid waste as hydrogen sources, what all of these products have in common is that they generate dirty hydrogen, which needs extensive cleaning. We highly recommend using alkaline electrolyzers, especially simple and modular off-the-shelf component alkaline electrolyzer modeled after the HHO cell architecture, which we discuss in a separate video. These simple electrolyzers, made using readily produced nickel electrodes and polyethersulfone diaphragm separators, can produce ultra-high purity hydrogen, where the only impurity is oxygen, which is readily removed. Conclusion. Thanks to the use of advanced insulation technology and its effective integration into the synthesis reactor column, the troublesome phenomenon of heat loss that has plagued small-scale production has been solved. Combining this with the exciting prospects of ionic liquid compression, what is awaiting us is a cheap, mass-produced, containerized, and extremely long-lasting ammonia production package, making obsolete the centralized hydrocarbon-based production method, which require immensely large and extremely difficult to manufacture components. The opportunity to exploit widely available commercial off-the-shelf equipment and components should not be overlooked. The use of a component-centric design philosophy, as well as standardization of small-scale ammonia equipment, where instead of each plant having a different design with its own peculiarities and idiosyncrasies, each plant behaves in a predictable manner, where spare parts can be readily interchanged. The improved use of modularity, off-site manufacturing enabled by containerization, and improvements in compressor technology culminate in a viable and competitive fertilizer and fuel production package. The anticipated capex, excluding any power source for the miniature ammonia plant, is only around $25,000 to $50,000 for a 100 to 300 ton per year system, excluding solar farm and electrolyzer costs. This number is very realistic, since we know that industrial-scale plants are in the range of $1,000 to $1,500 per ton per year, and since the miniature plant can use off-the-shelf components and requires no specialized equipment for erection and site preparation, and is much less labor-intensive, this price is probably overly conservative and could be reduced to $20,000 under an aggressive high-volume manufacturing regime. From a basic material usage perspective, a technology is being efficiently produced if it sells for only a small margin above material costs. For example, raw material costs comprise 80% of the cost of modern lithium-ion batteries, suggesting there is little room to improve their production economics. For a 100-ton per year plant, the weight of the unit, including only the core reactor and heat exchanger module, weighs less than a ton. Including a solar farm at $500 per kilowatt and low-cost alkaline electrolyzers at $50 to $100 per kilowatt, the total capex is projected to be below $3,000 per ton per year, while the plant itself is only $200 to $500 per ton per year. At an ammonia price of $800 per ton, the payback time is only 3.75 years. Over a 20-year period, the levelized cost per ton of ammonia could be as little as $135 using solar energy. At the current NH3 price of $1,500 per ton, the payback time is only 4 months. Beyond that point, the plant would be free, with the only cost being annual maintenance and the eventual regeneration of the electrolyzer stack. The uncertain future of natural gas and coal make the development of electrolytic-based hydrogen to ammonia a near requirement in the coming decades. It is likely that in the future, numerous companies will offer compact, containerized, modular, ready-to-install plants at affordable prices by applying assembly line mass production methodology to chemical plant manufacturing. It is anticipated that China will dominate the industry, taking market share away from established Western companies like Casole, Halda Topsoe, KBR, and ThyssenKrupp Industrial Solutions. The competitive advantage established by these producers is attributable to the high level of technical expertise, manufacturing difficulty, certification and regulatory knowledge, and the intellectual property and proprietary knowledge they possess. Distributed production overturns this paradigm, paving the way for a more competitive and consumer-friendly landscape where farmers, rather than producers, enjoy the upper hand. Note: most of the price quotes were received from Chinese companies. This isn't due to some nationalistic preference, but rather due to the convenience of being able to quickly request quotes on online marketplaces such as Alibaba, which have an efficient RFQ request for quotation service. It's very difficult to source accurate price estimates from upscale Western manufacturers, as they don't bother giving out quotes to anyone but the most serious buyers. There are few Western firms advertising on Alibaba. Additionally, most of these large Western companies, due to their prominence and industrial dominance, are far too busy to spend time giving out quotes, let alone selling small quantities of a product, to those who aren't necessarily credible prospective customers, namely small organizations. This is largely due to the reduced market competition they face, compared to the ultra-competitive landscape in China. Secondly, we believe the prices in China are more reflective of the inherently lower production cost that can be exploited with global manufacturing, thanks to modularity and the absence of site specificity. All the components in the miniature plant, except for the exotic metal organic framework part petroleum gas purifier, could be sourced from China. Current Chinese manufacturers are not yet able to build high-purity filters, and this technology was sourced from Western firms instead. The ionic liquid candidate for the compressor can be sourced on Alibaba as well for a reasonable price of $600 per kilogram. In conclusion, there are no proprietary, patent-protected, highly specialized, exotic, or extremely niche technologies found in an ammonia plant, let alone a very small one. All of the critical parts, raw materials, components, and their concomitant manufacturing processes can be easily handled by legions of generic companies which advertise on online marketplaces such as Alibaba or IndiaMart. This is an excellent condition, since it allows for a democratization of technology away from monopolistic firms. We hope you enjoyed this video. Be sure to visit Pichari Technologies YouTube channel for more valuable information on emerging and novel technologies.